Hello, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, so let's wait for 2 to 3 minutes more. So start at 8:10.
Ma'am, will you clarify a doubt in meanwhile?
Yeah, sure.
Ma'am, quiz to mock test is there, right?
Yeah.
Could you solve fifth question?
Uh, Actually, I don't know your fifth question and my fifth question was on this. Can you paste the screenshot of the question in the chat box? That will be much better.
2 minutes, ma'am.
Yeah. So,
Ma'am,
okay, so
have you seen the quiz to question paper?
yeah, I have seen the question. Is there
What
any
is your
confusion?
opinion? What is your opinion on that? It's easy, moderate, or
I think some questions are moderate, and although it's easy to score a good interest. What is you guys think? It's my
moderate,
opinion.
moderate paper, moderate.
Moderate only,
Easy,
na?
ma'am.
It's
Some sort of easy.
easy
Easy
mostly.
to moderate.
Right. I mean, it's not that
Can
difficult. Yes,
can you
Priyanka.
explain some questions?
Can I explain which questions?
Ma'am, in which differentiability is asked? Question number.
Ma'am, in the question which she is asking, the log x
Mhm.
graph is differentiable in the
Ma'am,
interval.
question number 8. Ma'am, question number 8.
Ma'am, I have doubt in
This
question
one,
number 7.
modulus of log of 1 plus x.
Ma'am, I am asking this one. That the first one
Okay.
is correct. I know that because the domain is minus in
Yeah,
1 comma
this one,
infinity.
na?
Hmm.
The domain is -1 comma infinity, and also told you
Hmm.
how to find out the
Because
graph of.
log 0 equal to 1. It's a
Uh,
hmm. And infinity can be any value of log. But in
right,
the
right.
interval,
Hmm.
log is 1 because it's a it's a strictly greater than and strictly less than interval.
No, 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 no. That's the reason. Here mod is there. So I also told you. See, this is the graph of log. If you shift it one unit toward left hand side, then the graph of log of x plus 1 will become this one, right? And if you apply the modulus, it will become something like this. So now here and at this interval, if you draw on any horizontal line, then it will intersect 2 points. So that's why it's not a 1-1 function.
Will it
But
touch
it's
the
showing that f
origin or
is
not?
not a 1-1 function. Yeah, sorry, what?
Will it touch the origin or like this?
No, this will be a point. Yeah, this will be an origin, correct. means something like this. It will grow something like here and then.
Ma'am,
But still,
but
again, it is not 1.
log 1 plus x is the entire function should have one graph. But
But modulus is there, na? So modulus,
hmm,
what it will do? It will just
hmm,
project all those things which are here in the negative section. It will
hmm,
say that
it will
you guys
project
will
in the
go up.
positive one. Oh,
Positive. So this scenario we already
oh,
discussed, I think, in
just
revision session.
just a small mistake done by me.
Yeah, that's okay. So what's your doubt, who sent this?
She asked
Manisha?
about
Question
question
number
number
8.
8. Here also my one option
Manisha.
doubt. Though these two questions I have made wrong also. And
This
rest of the
last
things,
sin x.
hmm, I
Okay, so
made
what's
just one option correct for both the ones. If I left only with one, then some marks
see
I should have.
f will be differential. You just have to apply the definition here only. So Priyanshi, you want to know about differentiability at 0, right?
Yes, ma'am.
So just apply left hand derivative and right hand derivative. So what will be left hand derivative? Left hand derivative will be limit h going to 0, f of a minus f of a minus h by h. Right? This is the general expression. So here in place of a we have 0. So just substitute all those things and just apply a hospital rule. I guess that's the thing here. So it will be 1 minus f of 0 minus h. That means f of minus h. And whenever x is not equals to 0, we have to adapt this expression, which is equal to sine of minus h upon minus h and then h. Right? So this will be same as limit h going to 0. Sine of minus theta will become minus of sine theta. So that's why this minus will jump here. And minus will get cancelled out. So ultimately it will become 1 minus sine of h upon h and upon h. So here if you take the LCM, we'll get a much simpler expression. H square and h minus sine of h. This is again 0 by 0 form. So here you apply a hospital rule to find out the limit. So limit h going to 0. If you apply a hospital rule, it will become 1 minus the derivative of sine will become cos h and it will become 2h. Again, you will apply a hospital rule because cos h will go to 1, 1 minus 1, 0. So that's why 0 by 0 case. So again, if you apply a hospital rule, you will get limit h going to 0. This will be minus of, sorry, plus of sin h because cos h is there. So derivative of cos h will become minus of sin h. So minus and minus plus. So that's why plus of sin h upon 2. Yeah, right. And this is equal to 0. So that's why left hand derivative equal to 0. 0 and similarly, if you calculate right hand derivative, it will be equal to 0. So that's why it will be differentiable and the derivative is equal to 0. So Priyanshi, where did you get confused here? What is the problem?
Ma'am, I am not able to, at the exam, I am not able to find the left hand derivative.
See, left hand derivative easy. You just have to compute this limit. I already told you derivative continuity is just a matter of limit. If you are comfortable with limit, there's nothing about derivatives. So it's just computation of a limit of this limit. Is
Ma'am,
that
I
fine for
have just
everyone?
posted a
Yes, ma'am.
Yep.
Okay. Yes,
Ma'am, I have
Yogesh?
pasted a question. Can you please explain it in chat box? I have
Yeah, so if we go with this thing, some questions, then it will take a time.
yeah, I think
Okay,
it
so
will
Ma'am,
take
Manish, this is your question.
ma'am.
Hello?
Yes, ma'am. Did you
Yeah,
call
ma'am.
me?
Yeah, I got the question. Actually, it will take a little time. So I'll
Okay,
start
no
with the
problem.
theory and
Yeah,
after
that's
we'll
better,
solve
ma'am.
all
Yeah,
these
we'll
questions.
do it later.
okay, ma'am.
So let's go to the theory of week 10 because week 10 has a lot of
Hmm?
concepts. So
Because
so
it's a
it's
new
better
thing
to
in
go
the
with
week 10
this.
graph theory.
Ma'am, is it connected to like CT? Can we say some sort of connection is there between
CT,
graph theory?
yeah, some sort of connection is there because ultimately you will use graphs and algorithms in CT, I guess. I mean, graphs and algorithms. Here you will learn algorithms in more mathematical fashion. So in CT, I think I don't know actually, but see,
Yeah,
let's go.
there is depth first in even CT.
Oh,
That's why I
DFS
was.
and DFS.
Uh, yeah, continue, please.
No. This is not the session for discussing quiz 2. So I'll first cover the graph theory part, hopefully for 6 to 7 lectures, and then we can discuss the quiz 2 paper. Okay, so let's start. So first, understand what is the graph and why we needed the graph. So actually, graph is a very easy way to denote the relation part. So relation means if you have any relation. So what is a relation? So relation on a set is nothing but a subset of S crosses. So if we have a set S, then a relation is nothing but a subset of S crosses. So that means from a set S, if you take the collection of any pairs, any type of pair A comma B, where A and B is a part of S crosses, or you can take any two sets here. That means A comma B is also okay. So a relation is nothing but a subset of a Cartesian product. Now we can actually formulate a graph related to this particular relation. And how we do that? So first understand what is a graph. So graph is actually a you can say a mathematical object. We can consider it. So a graph it involves two type of things or two sets we can say. So graph G is graph is denoted by in generally G, and it is nothing but a collection of two type of sets V and E, where V is a set and V is a set. It is any set. So you can take V as a set of peoples, V as a set of countries, V as a set of anything you want. So V is a simple set, and this is known to be the set of vertices. Set of vertices. So whatever object will collect in this particular set V is known to be a set of vertices. And here E is any subset of V cross. So E is a subset of V cross V. So ultimately you can say that E is nothing but a relation on V cross V, because we know that a relation is nothing but a subset of S crosses. So this E can be easily, we can easily connect any relation with this subset E. So that means this E is a relation on V cross V. And this is known to be the set of edges. And why it's known to be a set of edges, so we will see now. So there is one way to express the graph, and that way is pictorial way. So whatever vertices you will have here in the set V, you'll just denote them by nodes. So here these black nodes are the set of vertices. And suppose A and B are related. So suppose there is an edge between A and B. If this pair belongs to belongs to the set E, then we'll just draw a line with an arrow pointing towards the vertex number B. So that means there will be an edge from A to B. So this is a one way, the pictorial way to denote a graph. So in short, a graph is nothing but a collection of two sets. G is nothing but a collection of two sets, V and E, where V is any set, and this is known to be the set of vertices, and E is the set of edges. And we will denote that there is an edge between a vertex A to B if we will say that this pair A comma B belongs to E. Right. So this is the mathematical way of saying that there is an edge from the vertex number A to vertex number B. And here observe the direction. We are saying that A comma B belongs to E. So that means there is an edge from vertex A, starting from a vertex A and ending at a vertex number B. So this is a graph. Now suppose you have a relation R. So suppose I have a relation R. Now using this relation, we can actually form a graph. And how we will form a graph? So suppose this is a relation, so obviously it will be a subset of some S crosses. So suppose R is a relation and it is a subset of S crosses. Then to formulate this relation in terms of graph, what we will do? In graph, we have to consider two things, either the set of vertices or the set of edges. So here we will take set of vertices to be nothing but the set number S. So we'll take V to be equal to S, and we'll take the set of edges is nothing but whatever pair this relation R contains, that will be our set of edges. So in that way, we can actually formulate a relation into a graph. So that means this is a vice versa condition. So if you have a relation, you can form a graph. If you have a graph, you can actually precisely say what is the relation related to that particular graph, because you have to take all those pair which has edges in between. Okay, so there are two basic relations discussed in the lecture. So one is the teacher-course relation. So if you have a class, so in that class, if you collect the teachers teaching some courses, and if you collect the courses too, so combining these two sets, so suppose we have a teachers. So suppose I have T1, T2, and T3, three teachers, and T1 teacher and T2 teacher actually teaches maths. Right. T2 and T3 teaches science, and T1 also teaches Hindi. So here what I can do to formulate this situation via graph, I'll take T1, T2, T3, maths, science and Hindi as my vertices, and whatever relation is there, and that relation I'll take as an edges. So that means I'll take nodes to be equal to T1, T2, T3, and subjects to be equal to math, science and Hindi. And whoever teaches which courses, we can just point out the end. So in this way, we can actually formulate a relation. We can actually formulate a graph using some, if you have some real life situation, there also we can formulate a graph. That's the main meaning here. Now, let's discuss some of the basic terminology. So what is a path in a graph? Okay. So is the graph definition is clear? Graph is nothing but set of vertices, set of edges. What is set of edge? It will be a subset of V cross. Okay, fine. Now let's go to the path. So what is a path in a graph? So what is a path? So path is nothing but a sequence of vertices. So before path, let's understand what, okay, we start with the path just. So what is a path in a graph? It's nothing but a sequence of vertices which are connected by an edge. So that means a path. So a path from the vertex V to a vertex U is a sequence of vertices, right? So we have to collect sequence of vertices connected by an edge, connected by edges. So what does that mean? So suppose you have a graph, something like this: 1, 2, 3, 4, 5, 6, and 1 is also connected to this, and suppose 7 is here. Something like this, you have a graph, right? So here, what will be the path between 1 and 7? So it's kind of obvious if you collect this sequence 1, 2, 3, and 7, then this is a sequence of vertices, right? Sequence of vertices. And here, the next vertex is connected to the previous vertex via an one edge, right? So 1 is connected to 2 via this edge, 2 is connected to 3 via this edge. And similarly here also. So that means every next vertex is connected to the previous one via a single edge. So such kind of sequence is known to be a path. In graph theory, generally we do not repeat an vertex in a path. So for example, if you take suppose this is also connected. So if you write one sequence something like this, that 1, 4, 5, 6, and then also go to 4, then we cannot say that this is a path from 1 to 4. Okay, because it's actually revolved once here and we are repeating the vertex 4 in between. So that means we are repeating a vertex in a path. So this is not the general case in graph theory. So whenever we have such kind of repetition of a vertex in a path, then that sequence is not a path, it will be a walk.
But ma'am, can we say here that it's a path from 1 to 6 instead of 4?
Yeah, so if you break the sequence here, then this will be a path from 1 to 6. But you have to take this only sequence, 1, 4, 5, 6. If you take 1,
Because
4, 5, 6, 4, then this is not a path.
because connecting the path to 4 again, this is a mistake done by us, I think.
Means?
Why should we connect the path with 4 again? Because we already include 4 in the path.
Yeah. So that's the thing that, see, suppose we have such kind of scenario. I mean, in general, in path, we do not repeat the vertex because repetition means we are actually coming at the same position via some edges also. So here also doesn't make sense to go into this cycle. If I just want to reach from 1 to 4, I can just use the single edge. I don't have to reach here and then go again the cycle and also reach here. So that's the meaning. In a path, we generally do not repeat the vertex because such kind of scenario can happen. It'll just take one cycle somewhere. So that's why in path, we do not repeat a vertex. In walk, we can repeat a vertex. Okay. So you can take another example too. So suppose
Ma'am, walk we can repeat. What is that? Can I repeat again?
yeah, sure. So suppose I have a graph like this. Right. So here I'll give you two sequences. from reaching the vertex number 6 to vertex number 7. So one thing I can do, I'll follow this sequence. That I'll start from 6, I'll go to 2 and then go to 7. Now this is a path, right? Because it is a sequence of vertices, and each next vertex is connected to the previous vertex via one edge. So that's why it will be a path, and it is not repeating any vertex. Now here, if I tell you that from 6 I'll go to 2, from 2 I'll go to 4, from 4 I'll go to 3, then go to 1, then go to 2, and then go to 7. So here what is happening? We are just taking one cycle here and then going to 7. So here what is happening? In between, I am repeating one vertex number 2. So now this won't be a path, because again, it is a sequence of vertices, and every next vertex is connected to the previous one via a single edge. So that means the sequence is correct, but here the only thing is happening is a repetition of vertex. So whenever such kind of thing happens, so we say that this sequence is not a path, but we can talk about a walk. So this will be a walk. So this is a little difference between path and walk. In walk, you can repeat a vertex. In path, you cannot repeat a vertex.
Ma'am, so all paths are walks, but all walks are not paths.
Walks are not path. You can say that, yeah.
Ma'am, could you repeat what did you say just now?
See, you say that every path is a walk. Every path is a walk. Because in walk, we just have a freedom that we can repeat a vertex. We can actually move from that vertex and again come back to that vertex. This is freedom we have. But in a path, we cannot do that. We have to go in a one direction thing. We cannot repeat that vertex again. Is
Understood.
that clear?
Yes, ma'am.
And path and walks are nothing but a sequence of vertices. We have to maintain one sequence, and that sequence of vertices should satisfy the property that the every next vertex should connect it to the previous one via a single edge, right? Because then only we can move. If you take a sequence like this, so suppose I'll take 6 and 4, and then 3 and 1, then this doesn't make sense, right? Because you cannot go from 6 to 4 using only one edge, right? You have to go to 2 and then go to 4. So this is basic definition of paths.
Ma'am, the sequence is important, right? You can't jump from one vertex to another.
Right. Sequence is important, that's fine. Because it satisfies the property that every next is connected to the previous one via a single edge. Single edge should be there.
Okay, ma'am.
Ma'am, could you repeat
Okay.
what you said one step back
See,
again?
I told that if you consider, I told you that path is nothing but a sequence of vertices, right? So here we have 7 vertices. So if I take this sequence, suppose I'll tell you that 6, 4, 3, 1. If I take this sequence, then this is a sequence. But here what is happening? 6 and 4 is not directly related. 6 and 4 are not directly related, right? There is no direct edge between 6 and 4. So you cannot say that this sequence corresponds to a path. Okay, is that fine? Because you cannot go directly from 6 to 4. You have to take one in between vertex, and that will be 2. So if you write 6 to 4, 3, 1, then yeah, this is a path from 6 to 1. Because we are going from 6 to 4.
6, 4, 3, 1 is not a path.
Yeah, 6, 4, 3,
meant
1
to
is
say.
not a path.
6, 2, 4, 3, 1 is a path.
This is a path.
Okay, yeah, understood.
Because in real life, what is a path? We will just we'll take some landmarks too. From this cities you will go to this city, then this cities you will go to this city. You cannot jump because there is no path from reaching to the city number 4 from the city number 6 directly, right? You have to go to city number 2 and then go to city number 4. Is that clear?
Yes, ma'am.
Okay.
Excuse me,
So
ma'am.
this is
Ma'am, I have a
Yes,
small doubt. Like, where do we use this concept of walk and paths? Like, how do we use this?
yeah. So it can be thought of that as I told you that suppose we have a graph of a country or we have a graph of a state in which every vertex denote your city, and whatever road is there, that will be your edges. So if you want to find out that we can reach from one city to another city or not, so there we can actually say that it is sufficient to find out a path from this vertex to that vertex, right? We can actually formulate. So suppose we have a state. In that state, all the cities are our vertices, and whatever roads are there, that are our edges. Okay, so suppose you are in Madhya Pradesh or somewhere. So I'll ask you that is there a way from reaching to reach Bhopal from the city Indore or no? Okay. Indore, right? So can we answer this one? So what we will do, we'll just formulate this particular situation in terms of graph, and there we ask a question that is there a path from the vertex which denote the Bhopal city to the vertex which denote the Indore city, right? So that means finding a path can give us a solution to very so many real life problems. Or for example, I'll give you another problem is. Yeah, it's also related to travel only. So if you have a airline, if you are looking at a airline service, then in that service, you always want to know that from which city to which city I can travel, right? So this is
Okay.
a feasible type of thing. So there we will use path. And here also we don't want to why we want to look at a path instead of log, because again, starting from one city and after after coming back to the same city and then going along, this doesn't make sense, right? Repetition of city doesn't make sense. So that's why we
Yes.
want to find out the path, not the one. Okay, so finding the path between two vertices is actually a very basic question in graph theory. So for that, for this particular question only, we have two methods, BFS and DFS. These two methods actually answer the question of reachability. This is known to be the reachability question, that if you can reach from a vertex U to another vertex V or not using some path in a graph. Okay.
Okay, got it.
Now let's go to the connected graph. Okay, so what is a connected graph? So connected graph means if you can reach from any vertex to any other vertex using some path, then that graph is known to be a connected. For example, this graph is connected because we can reach to any vertex from any other vertex. So if I'll ask you, can we reach from vertex number 5 to vertex number 3? So the answer is yes. We can just follow the sequence. I'll start from 5, I'll go to 2, then go to 4, and then go to 3. Right? So this is one path. So in this path, you can actually reach from any vertex to any other vertex. But here, if I give you some graph like this, so now okay, so suppose I have this type of graph. There are 7 vertices and the edges are denoted like this. Okay, now this whole picture is your graph. Now here, we cannot reach to vertex number 1 from vertex number 5 or any of the vertex, right? These 4 vertices are, we cannot reach these 3 vertices from these 4 vertices, right? So this is not a connected graph because we cannot find a path between the vertex number 5 to 1 or any vertex which lies over this particular rectangle and any vertex which lies over this particular, a rectangle triangle. Okay, so such kind of graph are disconnected graph. But connected graphs example is this one. So we can actually reach from any vertex to any other vertex using some path. Such kind of graph is known to be a connected graph. Is that fine?
Yes, ma'am.
Ma'am, like the edges are missing or something. We can say it is
No,
a
no, no.
disconnected graph.
Yeah. That means some edges are missing, obviously. So if you add one edge here, so suppose I'll connect 1 to 4, then this will become a connected graph. Because now if you want to go to any vertex in this particular triangle, you'll just use this edge. So for example, I want to go from 6 to 3. Right. So what I'll do, I'll start from 6, go to 5, go to 4, then go to 1, and then go to 3. So now we have a path. So if we remove this edge, then it will be a disconnected graph. But if you add this edge, then it will be a connected graph. Now there are also two types of graph, directed graph and undirected graph. So this is the undirected graph situation. So let's understand what are the directed graph. Yeah, first understand what are the undirected graph. So in undirected graph, if you compute the relation or if you look at the set of edges E, then this will be a then this will be a symmetric relation. So this will satisfy the symmetric property. What is the symmetric property? Symmetric property means if there is an edge between A and B, okay, so if there is an edge from between A and B, then there is also, then this will imply there will be an edge from B to A2. So that means if we have a one direction edge, then we also have in another direction. So such kind of a scenario where we have, and this is for all vertices, not for one particular pair of vertex, but in between any vertex, if you can move into both directions, that means if you can go from A to B and B to A, then such kind of graph is known to be an undirected graph. So ultimately, there is no significance of direction. You can move in any direction, whatever you want. So this is for all vertices. So we can understand this by symmetry also. So if A comma B belongs to E, then simply implying that B comma A is also belong to E. And this is the definition of symmetry. So directed graph are those graphs where the set of edges are having the symmetric pairs too. So that means you can go from A to B and also go and also reverse it. That means you can also go from B to A.
This
So
is the
in
meaning
general,
of directed graph, right, ma'am? Symmetric, if it is symmetric.
undirected graph, because you can go from any direction to any direction.
Uh,
Okay.
no, ma'am, you just said directed, right?
No. This is the definition of undirected graph. Undirected graph means we don't have any particular significance of direction, right? You can go from A to B, and also you can come back from B to A.
Oh, okay. Sorry, ma'am. Yeah, understood.
Right. So there is no particular fixed direction. So what happens? So if you want to
Can you draw
denote
can you draw the diagram for a undirected graph and a
undirected graph,
directed graph?
yeah, I'll come to that.
For both of them.
See, so if you consider any pair here in this undirected graph, then what happens? There is an edge from A to B, right? And there is also an edge from B to A. So we have such kind of edges. So these edges, either you can denote it by two-sided arrows, or whenever we have two-sided arrow, we just simply replace that with a single line. So if you look at a graph with this particular single line, so the single line means you can move in any direction. So that means A comma B is there and B comma A is also there. So that's why undirected graph are picture like something like this. Only simple lines are there, as I told you earlier. So this is a one kind of undirected graph. 1, 2, 3. Now, what is a directed graph? So in directed graph, there will be one pair which does not satisfy the symmetric relation. So what is a directed graph? Directed graph means there will be at least one pair V comma U in such a way that there is an edge from V to U, but there is no edge from U to U. Okay, this is known to be a directed graph. Now, suppose this is the above one, this one, A, this graph A is actually an undirected graph. Now, what will be the directed graph looking same thing? So what you can do, you can actually take that there is an edge from 4 to 3, but we cannot go back from 3 to 4, and all other things are same. Now, this will be your directed graph. 1, 2. Because here what is happening, we can actually go from 4 to 3, 4 comma 3 edge is there, but 3 comma 4 edge is not. So this is the difference of directed and undirected graph. Is that clear?
Yes, ma'am. Thank
Ma'am,
you.
can you repeat again?
Yeah. See, directed graph means there will be one pair which does not satisfy the symmetric relation. Symmetric relation means there is an edge from V to U, but there is no edge from U to V. So for example, in this graph, there is an edge from 4 to 3, but there is no edge, no direct edge, obviously, from 3 to 4. So here the significance of direction is there. You can move in this direction, but you cannot reverse it. So such kind of graph is known to be a directed graph. But if all pairs have the symmetric relation, so that means if there is an edge from A to B, then there is also an edge from B to A. So that means you can go from A to B and B to A to B. Such kind of graph is known to be an undirected graph. And it's very easy to judge which graph are directed or undirected. You just have to find out a pair but does not satisfy the symmetric relation. Okay. Is that fine?
Yes, ma'am.
Any
Probably.
doubt?
No.
Yeah, it will get more clear as we go now. So now let's go to the next topic, which is graph coloring. So what is a graph coloring means? So here what is happening that in our graph, we have to assign one color to each vertices, but in such a way that if two vertices are connected by an edge, then they should get different colors. So graph coloring problem means we have to assign each vertex a color. So whenever we have such kind of assigning or mapping, we generally use the function. So if we have a graph G with the set of vertices to be V and the set of edges to be E, then if we can find out the function C, which will associate each edge to a fixed color. Okay, so suppose you have a set of color here. So suppose red, blue, black, white, whatever set you have. So for each edge, this is not edge. For each vertex, we have to assign a color in such a way that
Ma'am,
if two vertices are
here what E represent here? V represent vertex, E represent.
V represent vertex and E represent edge set. So we have to assign color for vertices. So for each vertex, we have to assign a color in such a way that if two vertices are related by one single edge, so suppose there is an edge from V to U, then this V should get some different color and U should get some different color. So for example, if I color this vertex number V with the red one, then I cannot use the red color for the vertex number U. I have to use some another color. So this is the one restriction we have to keep in mind when we color our graph. So such kind of process is known to be a graph coloring. Okay. So graph coloring means we have to associate a color to every vertices, but with a restriction. What is the restriction? We have to take care that if there is an edge between two vertices, then these two vertices should get different color. So that means, see here, we have an edge from V to U. So if we assign red color to V, so we cannot assign the red color to U. We have to take some another color. So let's take it to be blue. So we can assign a color blue to the vertex number E. So in such a way, we have to assign a color to every vertex of a graph. This is known to be a graph coloring. So now what is a one visible coloring? So one visible coloring is if you have 5 different vertices, we'll just give every vertex a different color. Then obviously it will satisfy this particular restriction because we were using every vertex has a different color. So it doesn't matter that two vertices are related or not. They always have a different color. So this is a one visible coloring. So that means there always exists a one visible coloring for color a graph. Now, what will be the question here? So the question will turn, okay, we have one solution, but what will be an optimal solution? Optimal means what will be the minimum number of color we require to color a graph? So this is the question we generally ask in graph color. So you have to find out the minimum number of color to color your graph. And what is the restriction? So this is a restriction. So if two vertices are connected by an edge, you have to take different color for these two vertices. Okay, is that clear?
Yes, ma'am.
Okay, now let's do some example, then it will be much clearer. So suppose I'll give you a graph. So suppose I have a vertex number 1 here. So I'll give you guys 2 minutes to answer this question. So suppose this is your graph G, then what will be the number of minimum, then how many color, what will be the minimum number of colors we need to color this particular graph with the restriction that if two vertices are connected by an edge, then we have to use two different colors. So what will be the minimum number of color we need here to color the graph? Okay. Minimum number of colors.
4, ma'am.
Okay, so 3, 4. Any other choice?
6.
Are you sure? 6. Minimum number of color we need.
No, ma'am.
Okay,
4.
okay.
4, 4.
4,
4
ma'am.
is the
4.
4, fine.
content the alternate
Okay, so
coloring.
let's find out. So let's find out. So what we do, so here since, there are methods to find out the coloring, but those are very advanced methods. So in our course, we just have to use our intuition. We have to use one color and try to force ourselves to stick with that color until and unless we reach a situation where we need to use another color. So for example, if I start coloring with any vertex, so let's start with the vertex number 2. So if I color this vertex with the blue color, then what can happen? So now you have to find out all the vertices for which you can use this particular blue color. Okay, so we cannot color the vertex number 1 with blue color because obviously these two are connected by an edge. We cannot use the blue color to the vertex number 3. So now we can use the blue color to the vertex number 4 because
4 and
they
6.
are not connected. Right? Similarly, we cannot use for 5, we can use for 6.
6.
Now there is no vertex which can be colored by the color blue.
Blue.
Correct? Now we
Oh.
come at a situation where we have to take another color. So let's take red. Now suppose I'll assign the red color to the vertex number 3. Now what are the vertices on which we cannot assign the red color? So obviously we can assign to the 5 because 5 is not connected
5,
to
7.
3 directly. Right? So we can assign 7. But again, we cannot assign the red color to vertex number 1. We cannot assign blue color to vertex number 1. So here we have to take another color. So suppose I'll assign it black. So that means for coloring this graph, I need at least 3 colors. Oh, sorry, right? 3 colors only, right? So the answer will be 3.
Okay.
So that's how we have to use. Just your intuition will help you. There won't be that much complicated graph where you need some algorithm or something else. You just have to go in this process. Take one color and color all the vertices which you can color with this particular color. And then if you need another color, then take another. Now suppose here in place of 7 vertex, if I have 8 vertices. So suppose here I have one more vertex. Suppose there is a vertex number 7 here, and then there is a vertex number 8 here. Then what will be the minimum number of color we need?
5, I guess.
5.
5. Sure.
Yes.
Okay, see. And sorry, this is also
4 only. Yeah.
4 only, right? Because see, we cannot use black color for 7 and 8 because they are related to this vertex number 1. But we can use red color to 1 and blue color to 1. So I don't think we need 4 to no, but we cannot use blue color because they are connected by here. So we need red 1. We can assign red here, but again, we cannot assign red, blue, or black to vertex number 7 because 7 is connected to this vertex and it has color blue. 7 is connected to the vertex number 1, it has color black, and 7 is connected to vertex number 8 and it has color red. So we have some kind
Introduce
of
new one.
circulate ourselves. Yeah, we have to use one another. We can use yellow. So that means the answer will change from 3 to 4. So here you observe a pattern. So the pattern is if you have even number of vertices with such kind of scenario that one center vertex is there and all other vertices are some kind of in circumference. So then actually this coloring depend on the number of vertices. Either they will be even or odd. So I'll leave to you guys what will be the cases. If you have even vertices, then how many colors you need. If you have odd vertices, how many colors you need. Okay, but this is a very simple and generic example for a graph.
Ma'am, a vertex can be connected by two same colors, right? Like red is connected by 2 blues. Is it true? Can we say?
Yeah, that will be fine. That will be fine. There is no restriction on. So only one restriction we have, that if there is a direct edge from a vertex number V to vertex number U, then you have to assign these two vertices to be different color. It is okay that if you have same color for this vertex. That's why we need minimum number of color, and this situation is okay. We can two blue surrounded by one red surrounded by 2 blues.
And what if there's no edge connecting to vertex number 7?
If there is no edge connected to vertex number 7, something like
what
this,
then?
yeah, then you can use any color to vertex number 7. You can assign red,
Can
you
we
can
use the
assign blue.
repeated color?
Yeah, we can use, because see,
Blue,
7
red,
is not
black.
connected to anyone, so it won't harm our restriction.
So if it's connected
Only
to any
one
color,
restriction.
you can't use that color.
Yeah, we
Okay.
can't use that color. Is that fine?
So what is the max which deals with graph coloring for advanced graphs, complex graphs?
Actually, there is a This is known to be a chromatic number. If you know something, this is a little advanced topic in graph theory. So they calculate one chromatic number, and then that chromatic number is actually the minimum number of color we need to color a graph. And to find out that chromatic number, they have several ways to find it out. And one advanced theorem is that four color theorem. So if you have any planar graph means any graph which you can draw in such a way that there is no cross section between an edges. So for example, if you have this graph, then it look like it is a cross section here, but we can actually draw it in different way. So what we can do, we can take this to be a cross edge, and this we can draw it like. So such kind of graph is known to be a planar graph. Planar graph means you can draw it on a paper, and there should not be a necessary cross. Such kind of graph is known to be a planar graph. So if you have a planar graph, then you actually need only four colors to color such kind of graph. So this is known to be a four color theorem, which are already, I think, introduced in the lecture too. We have a map. So we have a map of India, and there we have to assign a color to each state, but in such a way that two neighbors will get a different color. So that will be a planar graph, and there we just need four colors. So there are several theorems to deal with graph coloring. Something like this. Color theorem.
What if it is a complete graph, like each vertex is not connected with each other vertex?
Then it will be a disconnected graph, right?
No. I mean, there are n into n minus 1 by 2 edges. But all the let's say we will take a simple of 5. So 5 vertices, all of them are connected to all. So in that scenario, actually we cannot use the minimal number of colors, right? So in that scenario, how many vertices are there? We have to have those number of colors. Is that correct?
Correct. Because every vertex is connected to every other vertex. So we are for following the restriction, we have to take that number of colors.
Ma'am, could you give an example?
Yeah. So for example, we have 5 vertices here. And suppose these 5 vertices are connected to each other. I mean, every vertex is connected to every other vertex. So we cannot draw like this. It will be a pentagon, I guess. So now in this graph, what is happening? Every vertex is connected to every other vertex. So now here, if I start coloring this graph and I'll assign the yellow color here, then I cannot assign yellow color to 5, cannot assign yellow color to 2, and also cannot assign to yellow color to 3 or 4. Correct? Because they all are directly connected by an edge. So I have to take another color. So if I again assign red here, I cannot use red to any of the vertex. So suppose I'll take some another color here, then this is not red, okay? So suppose this is pink.
So ma'am, we can say that here we have to use 5
the
distinct
number
colors.
of vertices, right,
5
5 distinct color we have to use. So such kind of graph actually has very big name. They are known to be a complete graph. So complete graph means in which every vertex is related to every other vertex via single edge, connected to every other vertex. So this kind of graph is known to be a complete graph. Okay,
so
because
this
here the
is
set
every edge.
Yeah.
I mean, every knot should be the different color, right?
Every knot should be the different color.
But green color twice, red color twice is there.
No. This is not red. This use think like this is pink or something. Golden
Okay,
or something. This is also not pink. Okay. Such kind of graph is known to be a complete graph. Complete graph means every vertex is connected to every other vertex via a single edge. Yes, Aditya.
Ma'am, could you prove maximum number of edges is n into n minus 1? Could you give an example? Proving that statement.
Maximum possible number of edges. So
yes, ma'am.
What is happening? If you have n number of vertices,
and 10 edges.
So suppose we have n number of vertices, then what will be the maximum number of edges? Again, this result is for undirected graph. That means if there is an edge between A to B, then we are assuming that this is a symmetric. I mean, this edge will work in a both direction. So in an undirected graph, if you have n vertices, then there will be at max n into n minus 1 by 2 number of edges. Right? Why this is a condition? Because here we are considering two facts. That first fact is this is an undirected graph. Okay. And the second fact is we are not considering the self loop. Self loop means we are not considering an edge whose starting point and the ending point is same. Such kind of
Ma'am,
edges.
ma'am, we can define edges as the two critical points of the line.
No, not critical point actually.
मतलब कि
No,
दोनों
critical point is not.
एक मतलब कि दो किनारे
Yeah,
ऐसे
end
बोल
point you can say. End point of an edge. Okay. So we are not considering the self loop. Now here, suppose you have n vertices. Now we have to find out at max what are the number of edges. So suppose I'll list out n vertex. So 1, 2, 3, 4, up to n vertices. Now what happened? This one is connected to every other vertex. So if one is connected to every other vertex, how many edges are there? There will be n edges related to one. So again, I'll repeat, here we are finding what is the possible number of, or what will be the maximum possible number of edges we can have in an undirected graph. Okay, so it is possible that every vertex is connected to every other vertex. That means one is connected to every other vertex. So that means one will take care of n edges, correct? Now here, let's assume that 2 is also connected to every other vertex, but if there is an edge between 1 and 2, then this edge is counted by 1. So now 2 will take care of n minus 1 number of edges. Okay, and similarly 3 will take care of n minus 2 number of edges. And in this way, if you process at the end, when you come to n, then n is automatically connected to every other vertex. So here we'll just take 1 edge. And now if you sum it, then it is nothing but n plus n minus 1 plus up to plus 3 plus 2 plus 1. And we know that this is the sum of first n numbers and it is equal to n into n minus 1 by 2. Okay, so this is a little proof. Is that fine, Aditya?
Yes, ma'am.
Yeah. So that means in an undirected graph, at most, we can have this many number of edges. We cannot cross this number. I mean, we cannot have a graph which will have more than this number of edges. So for example, if you have 5 vertices, so with 5 vertices, we can have at most 5 into 5 minus 1, that will be 4 by 2, which is 10 edges.
10.
And which is this particular graph, pentagon. So here, if you calculate, there will be 10 edges.
Yes, Christmas tree.
Ma'am,
Right.
how can it 10 edges? 10 edges?
Yeah, count
let
it.
me
It will
let
be
me
10
count
edges.
it.
Yeah, you will count. Okay, so and let me know if there are 10 edges. Because there will be 10 edges. Now let's go to the
There are 10 edges,
next
ma'am.
concept. Okay, fine. Now let's go to the next concept, which is the independence. Now let's start with vertex colorings. Is there any
Ma'am,
doubt in
edge.
graph coloring?
So if there are present 10 edges, then edges are not the endpoints.
Edges
Edges
are
are
not endpoints. Edges are pair of
edges are
vertices.
the arms. We can say
I
the
don't know,
arm
we
of a
can say that or
triangle.
not.
We can say that the
Yeah,
arm of a
obviously
triangle.
edge. Yeah, arm is same as edge. There are different names. Now, there is one concept. So suppose what are the adjacency vertices? Okay, adjacent vertices. So adjacent vertices means if there is an edge from a vertex to another vertex, then we say that these two vertices are adjacent. Adjacent means a neighbor, you can say. So suppose there is an edge from a vertex number V to vertex number U, then we say V and U are adjacent. V and U are adjacent. Adjacent means some kind of some kind of neighbor type of behavior. If they are directly connected by an edge, we'll just say that these two vertices are adjacent vertices. Now, what is a vertex cover? So in vertex cover, we have to collect, the vertex cover is nothing but again a subset of vertices. So a vertex cover is a subset of vertices. subset of vertices which will cover all the edges. Now, what is the meaning of this sentence, that which will cover all the edges? So if you have an edge in your graph, then that edge will have endpoint belong to this particular subset. So for example, if this is an edge E, so then there will be two endpoints here, A and B. So one of the two endpoints should belong to your subset. Okay, and which subset? This particular subset, whatever we are considering. So this is known to be a vertex cover. So we are using vertices to cover the whole graph. That's the main purpose. So ultimately, we have to collect all those we have to collect vertices in such a way which will take care of the covering of an edges. That means if we have an edge, then of that edge there will be two endpoints, right? So at least one of the endpoints should belong to our given subset. So let's understand this by an example. So for example, if I have a graph something like this. Okay, so suppose this is a graph of vertices 1, 2, 3, 4, 5, 6, right? So what will be the feasible vertex cover here? Vertex cover, again, we have to collect some vertices, right? It is a subset of vertices. So suppose I'll take one vertex cover, VC1, and I'll take the vertices, namely 1, 2, 3, 4, 5, and 6. I'm taking all the vertices, right? Then this is again a subset of a vertex set V, correct? It is a subset. And it is actually covering all the edges. Covering all the edges means if you pick any edge, so suppose I'll pick this edge, let's name it to be even. So if you pick the even edge, then what are the endpoint of this edge? So endpoints are 3 and 4. And here the case is both are the endpoints are belonging to our subset. So this is a one type of vertex cover. Now in place of this subset, if I take another vertex cover, VC2, now here what happened, I'll just take 2 and 4. Okay. Now, in this particular graph, if you consider any edge, so suppose we'll name the edges to be E1, E2, E3, E4, and E5. Now here, let's start with E1. So E1 will have endpoint 3 and 4. So this 4 is belong to our subset. So that means E1 is covered. Now E2. E2 has endpoint 4 and 5. So this 4 is belong to our subset. That's why E2 is also covered. E3 has endpoint again 4 and 6. So 4 is belong to our subset. E3 is also covered. Similarly, E4 is also covered. And similarly, E5 is also covered because E5 has endpoint 2 and 1 and 2 belong to our subset. So that means this particular subset is a vertex cover. Okay. So vertex cover means, yeah, so vertex cover means a subset of vertices which will cover all the edges. Cover the all the edges means every edge will have two endpoints. So one of the endpoints should belong to your subset. Then we are saying that it is covering all the edges. Now this you can understand by the real life situation. So for example, if I put a camera here, if I put a camera at this intersection, then that camera will cover this corridor, these two corridors can be covered by this camera C1. Now, if you put a camera here, C2 camera, then this C2 camera will cover this corridor, and this corridor. If you have gone through the lecture, then there we illustrate vertex cover in this fashion. So suppose we have a hotel, and in that hotel we have to insert some CCTV cameras. But the thing is, if we insert one CCTV camera at the intersection means suppose these are the corridors. So if you insert one CCTV camera here, then this CCTV camera will take care of this corridor, and this corridor. So similarly, we have to find out the proper number of places or proper number of intersection of corridors where we can put the CCTV cameras. So here, if you put one CCTV camera at vertex number 2, you will cover these two corridors. If you put one camera on vertex number 4, you will cover the rest of the corridors. Okay, so such kind of subsets are known to be vertex. Is that clear?
Ma'am, we can plant camera on 1 or 4. It will work now.
Yeah, it will also work. That's why vertex cover is not unique. It depends on your choices. But again, here we can always find out one vertex cover. So if I give you a graph, then what will be a general vertex cover? What will be the simplest vertex cover we can find?
4.
Any general graph, not this one. What will be the one possible vertex cover? We can take all
Completed
vertices,
cover
one.
right?
more edge or say more
We can take,
corridor.
yeah, so we'll take all the vertices. That will solve our problem. That will
Less
be
degree
one
vertex.
vertex cover. Right? This is the trivial one. Trivial vertex cover. We'll just take the set of vertices as our vertex cover. That will work. Because every edge will have endpoint in between the vertices only. Okay, what I mean by that. So suppose you have this, any graph you have, doesn't matter. Any graph. So suppose I have in general a graph G, which is a set of vertices is V, edges is V. So if I take V as a vertex cover, this will be a vertex cover, correct? The set of vertices, can we take this to be as a vertex cover? Reform the question. So if G is this graph with vertex V only, so the question is, does the set V work as a vertex cover?
Yes.
Yeah, it will work. Why it will work?
Because it is connected with the E.
Right, because if you take any edge, then this edge will have two endpoints, and those two endpoints are nothing but vertices. And these A comma B both belongs to E. So that means this set V will cover all the edges. That's the meaning of vertex. So that
It is
means here
symmetric.
we, yeah, correct. So whatever you have. So again, so that means one feasible vertex cover we have. Now, what will be the question here? So the question will be, what is the minimum number of vertices we can take and form a vertex cover? So again, we have to find out the minimum vertex cover. Minimum vertex cover means we have to consider minimum number of vertices and or a subset of minimum number of vertices, which will act like a vertex cover. Again, what is a vertex cover? Vertex cover means a subset of vertices which will cover all the edges. Covering all the edges means at least one of the endpoint of every edge should belong to our vertex cover. Okay, so now here the question is, what is the minimum possible vertex cover? So the minimal possible vertex cover is again, there are algorithms to find out minimal possible vertex cover, but here we just have to use our intuition. So for example, in the previous graph, if you consider a vertex cover, so here we have to find out the number of vertices, the minimum number of vertices we can use and form a vertex cover. So suppose I have this graph with again the vertex 1, 2, 3, 4. So I've not taken 4 here, I guess. So 4, 3, 5, 6. Okay. Now here, if I consider the set vertex cover to be equal to 2, 4, right? Then this set will work as a vertex cover. Will work as a vertex cover.
Yes.
Right. And here we are using just 2 vertices. So this is one fact we know. Now we cannot make a vertex cover using a single vertex. Now here we cannot form a vertex cover using a single vertex. Why is this so? So suppose I'll take one subset to be equal to simply the vertex number 4. Then is this subset a vertex cover?
Yeah, it is
Is
subset.
this subset? Yeah, it will be a subset. So
But
is
it's
this
not a
subset
vertex
is
cover.
a vertex cover or not?
No, ma'am.
Why it is
No,
not a
ma'am,
vertex
because
cover?
if
It's not covering all.
it not cover
covering all,
one,
correct?
ma'am.
Right. It will cover these 4 edges, but it is not covering this particular edge. So that
Yes.
means we cannot find a vertex cover here with a single vertex. So that means we need at least 2 number of vertices to cover our graph. So here,
Ma'am,
what is the minimum number?
in previous example or in coloring example where the center one is connected to all of the nodes, right? Can we say the center one as the
Is
only
the
single
vertex?
one?
No. Yeah, I'll come to that too. Single one is not, because there are edges over the boundary too, right? So we have to cover the boundary edges too.
Okay, now I understood. Okay, ma'am, understood.
Excuse me, ma'am.
Yes.
If we remove one from that graph, then 4 can
Then
work.
only, right. Then phone will work as a vertex cover, right? But in this graph, now we need at least 2 number of vertices to cover the whole graph. So this number 2 is actually important to us. So this is the one problem we have. So again, we want to find out the minimum number of vertices using which we can form a vertex cover. So this is a general question we will ask. Now, suppose I'll give you one example. So in this
Ma'am,
example,
this
let's take
vertex cover is a directed graph, right? Or
no,
undirected?
vertex. Yeah, you can find out vertex cover in any graph. Directed, undirected doesn't mean. But in general, we'll just deal with undirected. No, I think there are questions using directed graph too in your activity question. So again, vertex cover is not specific with directed or undirected graph. You just
Okay,
have to
ma'am.
cover all the edges.
Ma'am, but we can't use 6 as a vertex cover, na? 2, 4,
Yeah, obviously
6.
no. That will be a vertex cover, but that won't be a minimum vertex cover. Minimum means we just want a minimum number of vertices. That will be a vertex cover. Why it won't be a vertex cover? If you use 2, 4, and 6, then you are covering this edge, this edge, this edge, and all the edges are covering. So yeah, this will be a one vertex cover, but again, not a minimum one.
Oh, minimum. Okay.
Okay, so now, for example, suppose I
Excuse
have
me, ma'am.
this.
Ma'am, a small doubt.
Yes.
Can you please explain that again? That if we have a vertex in the center and it is connected to all other
Yeah. I'm coming to this example. So suppose we have such kind of graph. So suppose I have vertex 1, 2, 3, 4, 5, 6. Now here, what will be the minimum or how many vertices? What is the minimum number of vertices we need to form a vertex curve? What will be your answer?
1, ma'am.
1, correct? Because if you contain this particular vertex, so suppose I'll make my vertex cover to be equal to this particular set which contain the vertex number 1. Then this is obviously a subset of vertex set. And if you take this vertex, then every edge related to every edge which is there in graph has endpoint to be equal to 1, right? So we can cover this edge, this edge, this edge. All the edges are covered. So here the minimum number of vertex cover is 1. But what happens if we have some more additional edges? Then the answer will differ. So suppose we have this particular graph. Now here the answer will differ. What will be the minimum number of vertices we need to form a vertex curve? So here what will be the answer?
4, I guess.
Okay, so let's try. Because again, we don't have a particular method. We just have to go by intuition. So obviously we should contain 1. Right? Our vertex cover should contain 1 so that we can cover this edge, and these all edges. Now, there are some edges left over the boundary. So I'll take the vertex number 2 in my vertex cover. Then vertex number 2 will cover these 2 edges. Now I'll take vertex number 4 in my vertex cover. So that will take care of these 2 edges. And I'll take vertex number 6 in my vertex.
6 and 7.
No, it will take. Right. We don't need 7. Right? The 6 will do the work. So that means we just need 4 vertices to form a vertex cover. So, and this is a minimum number.
Why we don't need 7?
Because
since
now
7 is
all
covered by
edges
2
are
also,
covered.
right?
2 is also, right. So we are taking alternate. So I'll start with 2, then 2, 4, and 6. You can start with 7, so then 7, 3, 5 will work. So this is one minimum vertex cover. You can also take this set, that
1, 3,
5,
5, 7.
This will also a minimum vertex cover. So that's why the number is important. We are not focusing on which vertices we are using, but the number. What are the minimum number of vertices we need to cover our graph? Okay, that number is important. So the number is here is 4. We need at least 4 vertices to cover a graph. Is that fine?
So that means, ma'am, this minimum number of vertices, this will vary according to the type of graph we are dealing with. So we cannot generalize this that we'll need only 2 or maybe 3 vertices.
Right. Correct. It depends on the nature of graph. How many edges are there, how many vertices are there.
Okay, yes.
Excuse me, ma'am.
Yes.
Here, why we have taken 2, 1, 4, and 6 can also work.
2, 1, 4. Okay, so let's try. 2, 1, 4 if I'll take. Then using 2, these 2 edges are covered. Using 4, these 2 edges are covered. But how we will cover these 2 edges?
Ma'am,
These 2 edges won't be covered.
1, 4, and
we
6.
need 1, 4, and 6. Yeah, obviously that's the same, na? 1, 2, 3, 4, or 6, or 2, 1, 4, or 6. Both sets are same. We have sets here, right? So we don't bother about the order. 146 to 146, all things are same. But again, the number is important. There we need at least 4 vertices to cover such kind of graph. Okay. So we have discussed examples. Is there any doubt in vertex cover now? Just
No, ma'am.
understand the definition and that's all. Okay. Now let's go to the independent set. So what is an independent set? Again, we have to consider one subset of vertices. Okay, so it is an independent set. So an independent set is again a subset of vertex set V, subset of a vertex set V, in such a way that two vertices are not adjacent to each other. So that means in such a way that two vertices are not connected by a direct edge, connected by a single edge. Okay, so such kind of set is known to be an independent set. Independent set means if you are considering any subset, then in that subset, whatever vertices you are taking, those vertices should not connect it with each other by a single edge. So for example, suppose I'll take the same graph. Okay, so in this graph, if we consider, this is the vertex number 2, if we consider this set, so suppose I'll take the set contained to be 2, 1, 4, and 7, right? So this is one subset of vertices, correct? Subset of vertices, subset
Hello?
of V. What? Yes.
Am I audible?
Is there any doubt?
No, ma'am. Actually, whenever you are completing the topic, just tell us that what kind of question can be framed.
Oh, yeah, sure. Right.
Thank you.
So with respect to independent set, we have the question that dance program question, right? So I'll explain that too. So let's finish this example. So here, if you consider this subset, which contain the vertex number 2, 1, 4, and 7, then what is happening? See, 1 and 2 are connected with a single edge, right? There is an edge from the vertex number 2 to the vertex number 1 and 4 is not, 1 and 4 is also connected by a single edge, but 4 and 7 is not connected. So here, what is happening? There are vertices which are connected to other vertices with a single edge. So this won't be an independent set. So this is not an independent set. So instead of this set, if you consider the set which will contain 2, 4, and 6, right? Now this is again a subset of vertices. Now here, but here what is happening? These vertices are not connected to each other by a single edge. So such kind of subset is known to be an independent set. Okay, so independent set means again a subset of vertex in such a way that two vertices should not be connected by a single edge in that particular subset. So for example, here, this is not an independent set, but here, this is an independent set. Okay, so what will be the one natural independent set? Can you give me one natural independent set in this particular graph?
357.
357.
Yeah, correct. 357 is there. 357. But what happen if I'll take just one vertex? So I'll make a subset with one vertex. Let's name it to be 1. Or you can take any vertex. Let's take 7. So if you take a single vertex, then this is also a subset. And here, since there is no other vertex, we don't have to bother about this
But
particular
ma'am,
situation.
this is not a vertex cover, no?
We don't need vertex cover now. We are talking about independence. Both are independent, both are different description. Vertex cover is gone now. Forget about it. Gone now. Be there in independence. What is independence? Okay, so now this is a very general independent set we can have in any graph. That means you are just considering a one single vertex. And obviously there is no other vertex. We don't have to bother about the situation that these two connected are. So in any graph, we have one independent set using only one vertex. So as in vertex cover, we want a minimum number of vertices to cover the graph. In independent set, we want the maximum number of vertices to form an independent set. So that means what are the max number, what are the maximum vertices I can collect, and that set still form the independent set. Is that fine? Any doubt? Someone raise hand.
Ma'am, can you repeat what an independent set means?
See, independent set means any subset of a vertices is an independent set if whatever vertices you are collecting, they should not be connected by a single edge. For example, in this graph, if you consider the vertices 2, 1, 4, and 7, then 2 and 1 are connected by a single edge. Correct? There is a direct edge from the vertex number 1 to a vertex number 2. So that's why this is not an independent set. But if you consider the subset simply 2, 4, and 6, then here 2 and 4 are not connected by a single edge. Correct? 2 and 4 are not connected by a single edge. 4 and 6 is also not connected by a single edge, and 6 and 2 is also not connected by a single edge. So such kind of subset is known to be an independent set. Is that fine now?
Yes, ma'am. Thank you.
Any other doubt? Okay, so now let's talk about one example. So suppose we have to run an event. So in that event, we have several groups. So suppose there is one dance program in any college. So in that dance program, you have to select some of the performances. But the restriction is that if there are intersection between two dance groups, so suppose the dance group number 1, there are several groups. So suppose group number 2, group number 3, group number 4, group number 5, and group number 6. So suppose I have, so let's open this. So suppose in a college there are 5 dance groups, and it is possible that these dance group will have some members in common. So whenever there is a common member in between any two dance groups, we'll just add an edge in between these dance groups. Okay. So suppose these are vertices now. These dance groups are vertices, and we'll draw an edge in between two dance groups if there is a common member. So suppose there is one common member in between the dance group group 2 and group 5. So I'll just draw in one edge here. So suppose there is a one common member in here. There is one common member here. There is one common member here. And there is one common member here. Okay. So ultimately, what is the graph we are getting? So we are getting that 1 is connected to 2. And then this is connected to 5. And this 5 is also connected to 2. 1 is connected to 3. Okay, and 5 is connected to. So this is the graph we are getting. And here every vertex is a dance group. And if we have intersection in any two dance group, we are drawing an edge in between them. So that means suppose there is one member here. So let's name it to be Ram. So suppose Ram is a member of 1. Then Ram is also member of 2, 3, and 5. So that means Ram is a member of these 4 groups. So at least one intersection is there. Now, our program committee want to schedule a dance performances, but they want a restriction that if a one group perform in the program, then if some groups perform in the program, then there should not be an intersection. So that means they don't want a person to dance twice, right? So they want that one person will dance only, at least once only. They don't want a person to dance twice. That's the restriction they are applying. So now the question is, what is the maximum number of dance group can participate in this particular program? So again, what is the restriction? So restriction is if there is a common member in two dance group, so one of them can perform, but the other one cannot, because again we want a person to only dance once, and obviously. And also the restriction is that if a dance group is performing, means every member is performing of that particular dance group. Okay. So here what happened, if we choose in our dance performance, so suppose I'll make one schedule. So suppose this is our first schedule. So suppose this is our schedule number 1. So in schedule number 1, I'll say let's say that dance group number 1 is performing. Okay, so G1 is performing. So if dance group number 1 will perform, then the dance group number 2 cannot perform because they have a common members. Dance group number 3 cannot perform because again they have a common members, and dance group of 5 cannot perform because again they have a common members. So if I allow to perform dance group number 1, then these three dance groups cannot perform in our program. So the other choice is dance group number 4. Okay. Fine. So this is a one feasible schedule anyone can think. But again, what we want to give chances to maximum number of persons. So again, we want to find out, we want to schedule a program in such a way where maximum number of dance groups can perform. Okay. So if I schedule in this way, then only 2 dance groups will perform. Okay. But here, in place of that, let's take another schedule. So in that schedule, if I say that, okay, dance group number 3 is performing, dance group number 4 is performing, right? So if 3 is performing, 1 cannot perform, 4 is performing, 5 cannot perform, but dance group number 2 can perform. Okay, now this is a better schedule, correct? Because it is allowing 3 groups to perform, to participate in the program. But the previous one is just allowing two groups to participate in the program. So now here, whatever schedule we are making, these schedule are nothing but an independent set. Because here, if you consider the if you consider the set 1, 4, then this is an independent set. Why it is an independent set? Can someone explain?
Because which will not depend on other.
Because they're not connected
They are not connected, correct?
directly.
Because they are not connected. So that's why it's an independent set. Now the second one also, you observe that this is also an independent set. Because obviously 3 and 4 are not connected directly. 4 and 2 is not connected directly, and 3 and 2 is also not connected directly. So we have 2 independent sets, but what is the specialty in this independent set? We have more number of members in here. So this is the one problem we are dealing with. So in a graph, we want to find out an independent set with maximum possible number of vertices. Okay. Now you guys get the feel.
Yeah,
what is the independent set?
Good explain.
Okay. Any doubt?
Yes, no, ma'am. Like, is this the maximum possible way? Like 3,
Yeah,
4,
this is
2.
the maximum possible, because see, now let's try to let's try to get any other vertex. So here I cannot introduce 1 because 1 and 3 are connected. I cannot take 5 because 5 and 2 are connected. So yeah, in this graph, the maximal independent set will have 3 vertices only.
Ma'am, can we say that from starting from like to get the maximum result out in 100% accuracy, can we start taking the result nodes from where only single least are connected from there?
Correct. So least number of edges is associated to which vertex? You have to start from that. So that's why I start from 3, because 3 is the only vertex which has only one edge. Correct. 3 on vertex number 3 we just have only one edge. Similarly, vertex number 4 also we just have only one edge. In vertex number 2 also we have minimum number of edges. So whenever you want to form a maximal independent set, let's try to find out such kind of vertices which will associate it with minimum number of edges. So for example, 3, 2, and 5. Because if I take 1, then I have to discard these 3 vertices from my program. Correct? Okay. So now let's do one more example. So again, our favorite one, just draw a center here. Three, 4, 5, 6, 7. Okay. So this is the 7 vertices. Now I'll ask you to find out what is the maximal independent set. Okay.
One only.
Maximal. I don't want minimum. Obviously, 1 will be an independent set, but maximal. You have to consider. You have to take. Again, you want the maximal vertices to be a part of your independence.
6.
6. Okay. So what are those 6 vertices?
Yes, ma'am. 6. 2,
So what
3,
will be the
4,
set?
5, 6, 7.
2, 3, 4, 5, 6.
Except 1.
Correct.
Yes.
Correct. 2, 3, 4, 5, 6, and 7. Because all these outer vertices are not connected. Yes,
Ma'am, but they're connected to 1, right?
Yeah, but that doesn't matter. They are not connected directly, no. 2 is not connected to 3 directly. We want direct edge. We don't want it is connected to someone and then connected to someone.
No, ma'am. The dancers they are common from 1. They have to perform in 2, 3, 4, 5, 6, and 7, right? Like they can't perform, right?
Even that is also I was also thinking, yeah. So if he is connected with
Yes.
only one, so one dancer, So he cannot go with the other, right? At a time, because one guy is connected with all, so we cannot pull him out from other dance.
No. See, suppose there is one person and that is in this particular dance group number 1. Then you are saying that this is also in 6, this is also in 5, this is also in 4. Yeah, this is the case.
Any one of the 6 groups can perform, ma'am. Like 7 or
Yeah,
1.
at a time.
Yeah,
At a
at a
time,
time.
No,
yeah.
At a
actually,
time,
2 and 7 or 3 are not having the difference with each other, right? They can perform
but see,
same
the
time.
common man cannot be the same. So suppose there is a common person in 1 and 2, there will be common person in 1 and 3, but there are no common person in 2 and 3. So what you are guys saying that if there is a person which is common in group number 1, then that will be a person is also in group number 6. That's you are saying, right? But this is a
Yeah.
group, so there are so many persons. So suppose some Ram is there, and Ram is a part of group number 1. Ram is also a part of group number 6, but Ram is not a part of group number 5. One will have some other person. Let's name it to be Sham. So
Ma'am,
then
we
Sham
should
is a
not.
part of.
I think this is going on like probability now. Like
No, see,
we can't say now.
no. That's the restriction we are making when we are drawing the graph. Graph says you will draw an edge if there are common person in between those two groups. So if Ram is here and Ram is also here, then I will draw an edge here too. Are you getting my point?
Could you repeat once again?
See, what these guys are. I mean, what you guys are thinking
Okay,
that
ma'am, I got
if
it now.
there
Yeah,
is,
yeah.
got it, no?
Yeah, if
So
a
see,
single guy connected means you have to draw edge from
draw an
every
edge.
edge.
So that's
Yeah.
why we are drawing an edges.
Now
So,
got it.
so that means if there is no edge between 6 and 5 means there is no common person in the dance group number
Correct.
6 and also in dance group number 5. There will be common person in 1 and 6, but those person are different. So here Ram is the person, but here the Ram is not the same person which is on what is number 2
Everywhere.
or the group number 5.
Yeah.
Ram is not everywhere. Yeah, Ram, yeah, whatever this is. So that's the thing. Because the graph, when we are drawing the graph, we are considering this restriction that if there is a common person in two dance group, we'll draw an edge in between them. So if we are not drawing an edge between them, that means we don't have a common person there.
Yes, got it. Yeah. If in this case, if you are drawing all the edges, then what is the case then?
Then what will be the independent set? That's your question.
Correct.
Yeah. So we'll find it out. So here in this case, the maximal possible independent set is 2 to 7. Okay. That's a good doubt actually. I also got confused for a moment. Is that clear, Manish, too?
And ma'am,
Yes, ma'am. I could understand. Like the same person is not there in 6 and 5, so we are not making an intersection. That means there is no edge. I understand.
Correct.
Yeah, got it.
Yes, Arvi?
ma'am, what will be the minimum independent set if we look for this question?
So minimum independent set means you will just consider one vertex. A single vertex will be there. That will be your minimum independent set.
Okay, so ma'am, we can like generalize this that minimum independent set will have one vertex.
One vertex, yeah.
Can
Because
one
this-
also be the minimum independent?
you
Whatever
can take minimum vertex to be 1, 2, or 3. Any vertex you can take.
You take one
That's why we
also.
don't. We can also take one also.
But 2 is connected to 7. 2 and 7 are connected to 1. No.
But that doesn't matter. We want, see.
Only one
if
is
you are
performing
taking
right
this
that day.
subset,
Need not worry.
So
Okay, so 2 and 7 are not directly connected.
not directly connected. That's why we need a direct edge.
Okay.
So connected means I'm repeatedly saying connected, but I should not say that. I should say adjacent. Adjacent means neighbor of each other, connected by a single edge. But again, we are not comfortable with adjacent, so that's why I'm saying connected by a single edge. Single edge should be there. Okay. Okay. So now let's take the problem that every vertex is connected to every other vertex. So suppose again I have 5 vertices, and these 5 vertices are connected to. Suppose that pentagon we have. Okay. So now here, what will be your maximal independence? because every vertex is connected to every other vertex.
I think only
That's
single
the point.
sets.
Single set.
If all edges are present, then only single edge.
I think
Right.
2, ma'am. 3 and 5.
Sorry.
You did not make a edge. Yeah, now it's fine.
I didn't make
Then
a
3
edge, so
only.
that's my mistake. Yeah, then 3 only or a single. Because obviously, if you insert any other vertex, then we are considering that every vertex is connected to every other vertex. So that these two vertices will be adjacent to each other. They are connected by a single. So obviously, in this case, the maximal independent set and the minimal independent are same, just only one single vertex. Okay, is that clear?
Yes, ma'am. Great explanation. Thank you.
Okay.
Excuse me, ma'am, a small doubt. Can we say that vertex 1 and 3 are adjacent vertices since they're connected by an edge, direct edge?
Yeah, correct. We can say. Because that's the definition of adjacent vertices.
Yes, ma'am.
What if there's an edge in between, like the star in between?
Means?
If there's another edge in between and all the other vertices is connected to that edge.
No,
as well.
center.
Oh, okay, center.
Vertex.
Then also the independent set will be the same, because again every other vertex is connected to every vertex is connected to every other vertex. So here also there will be only one.
Ma'am, in previous
But
example,
in this case,
the second last example, I guess, 2, 4, 6 or 3, 5, 7, which you have got.
right. That's the
In
same
that
thing.
one, yeah, that's the answer, I guess.
Now here, what will be the maximal independent set? What will be your guess?
2, ma'am. 4 and 6.
Maximal.
Maximum, yes, ma'am.
Yeah, I think 2 and 4. Yeah, 2
2,
and
4,
4 will
6.
work.
2, 4, 6, yes, ma'am.
But now 2 and 6 we cannot take together. Because 2 and 6 are connected.
Sorry. 2 or 4 or 3 or 5.
Yeah, I think there are only 2 vertices. Because if you take one, then we cannot take any other vertex. So obviously we should not consider one in our independence. So let's take 2. So if you take 2, then we cannot take 6, we cannot take 3. So that means the only choice will left, either we can take 5 or we can take. So if we take 4, then obviously we cannot take 5. So here the maximal independent set will be only 2 vertices.
Can we take 1 also, right, ma'am? Like in place of 4?
No,
2,
because 2 and
1.
1 are connected in single edge, right?
Because 2 is connected to 1 now.
2 is connected to 1. See, this such direct
Okay,
edge.
yeah, understood.
So it won't be independent.
So if you're taking 1, you can't take anything.
Anything else, correct? Because everything is connected to one direct.
Connect. Adjacent. Yes.
Okay, so now let's go to the next topic, which is our
This is like game of
matching.
intuition, right, ma'am? The graph, like plotting independence vertices.
I mean, yeah, you have to use intuition only, because see, algorithms are very advanced in this case for independent set, vertex cover, matchings, and all those things. So that's why, since we are in a foundational level, so we just use our intuition to find out such independent set and vertex count. Okay, there are algorithms, but those are very tricky, and forget about them. Let's go to matching now.
Hello, ma'am.
Yes, Shraddha.
Ma'am, can you take that from activity question 10.2, the games?
Okay,
in
so
which yeah, is it
so
possible
we'll
to
go.
take you now, or we can take it after, as you wish?
Yeah, so after 30 minutes, I'll take that question.
Okay, fine, ma'am.
Or else
Not
we
an
can take it in open session. Yeah, Shraddha, I also have one comment I forgot. So we'll discuss it at the end. You ask one question where we have such kind of thing, like log x, nx. This is the one question we discussed. And there I say that it will become 1 and we don't have to consider the restriction and all those things. if you remember.
Yeah, ma'am.
So actually I have made a mistake there. So we will discuss it at the end. Okay,
Yeah, sure.
So what is a matching? So far we are just considering the subset of vertices. Now what you have to do, we have to consider the edges which are actually covering all the vertices. So such kind of subset of edges are known to be matching. So let's define formally. So again, so what is the intuition of matching is, so suppose you are in your classroom. So in that classroom, someone gives you a project, and the condition of the project is that on that project, either two persons can work if they are friends, or either only one single person will work. So that means if you have a project, then this project, two persons can work. So suppose two A and B can work if these two persons are friends, right? Or else only one single person will work. So it is not the case that two person are working on a project and they are not friends. So now what we have to do, we have to make a feasible allocation with respect to this particular condition, that if two person are friends, then they can work on a project. So we can assign one project to these two persons, or we can take a single person and assign a project to them. And we want to find out much possible pairs of such a kind of friends. So what we'll do, we'll suppose we have a we again we'll take our graph. So in graph, what will be the vertices? So every student will be our vertices. So suppose we have some students here. So suppose again 1, 2, 4, 5, 6, 7. So suppose this is our required graph. So here what is the condition? So condition is the vertices are nothing but the set of students, and if there is an edge between two vertices, then these two students are friends. So that means since there is an edge between 2 and 6, so that means 2 and 6 are friends. There is an edge between 1 and 6, so that means 1 and 6 are friends. Okay, so this is a required graph. Now here we want to allot the project to project in such a way that if two persons are friends, then we can give them a one project. So here what we can do, so we know that 1 and 6 are friends, so we can give one project here. So we'll say that you two will work on project number A, project A. Okay, so I'll say 2 and 4, you guys will work on project B. Okay, but then 7 and 5 will have to work on different project, but individually they don't have any kind of support. So this is a one possible allocation we can do for projects and students. But here what happened, if we allot them in some different way means, suppose I'll say that okay, 1 and 2 you guys will work on project number A, and then
4 and 5
6
and
and
6
7,
and 7.
right, you guys work on project number B, and similarly C. Now this allocation feels a very comfortable, and it will give opportunity to everyone work in a pair. They have some kind of support, they can use another person, and they are friends, so they understand each other's behavior. Okay, so now this problem we can solve using the match. Is my screen visible? Yeah. So what is a matching? So far we are just considering the set of vertices. We are not bothering the edges. We are not bothering about the edges. But in a matching, what we have to do, we have to collect edges. Okay, we have to collect edges. But what will be the restriction here? We have to collect those edges which have distinct endpoints. So that means, so we have to collect those edges which have distinct endpoints. So that means, suppose I have this graph, and in this graph, if I consider one set of edges, so I'll name the edges two. So E1, E2, E3, E4, E5, and E6. Now here, if I collect edges in such a way, so suppose I'll take E1 and I'll take E4, right? Now this is a collection of edges, and this is a subset of edges. And here what is happening? What are the endpoint of edge number E1? So the endpoints are 1, 2. And what are the endpoint of edge number E4? So the E4 has endpoint 6, 7. That means these two edges are disjoint, disconnected. Or yeah, I mean they are not sharing any common name. So such kind of collection is known to be a matching. Now, this particular allocation is an example of a perfect match. So what is a perfect matching? So perfect matching is nothing a matching which will cover all the vertices. Which will cover all the vertices means if you take any vertex, then that vertex will be related to at least one of the edges in our required matching. So for example, here, if I take the subset to be this subset, E1, E4, and E6, right? Now, what is happening? So this one vertex is a part of a edge E1. So that means this is covered. As we are covering edges in vertex cover, similarly here we are covering vertices in matching. Okay. So this 1 is a part of E1, 2 is also a part of E1, 4 is a part of E6, 7 is a part of E6, 6 is a part of E4, and 7 is a part of E4. So that means all the vertices are covered by this particular matching. Now, such kind of matching is known to be a perfect match. Okay, so that means what is a perfect matching? So perfect matching is a matching. So that means every edges should be disconnected with each other. That means they should not share a common vertex. And every vertex should be a part of at least one of the edge in our match, as we want in our vertex cover. So in vertex cover, we want to cover all the edges. In perfect matching, we want to cover all the vertices of the graph. And again, one remark is that it is not always the case that you will find a perfect matching. So for example, if I go to our graph, the pentagon or the star graph, now here you cannot find a perfect match. So suppose I'll take any edge. So if you consider this edge in your matching, then these two vertices are covered, right? And then you can take, no, here actually we have a perfect matching because we can take this vertex, this edge. Yeah, so if we take this edge, then this edge, this edge, this edge, these three edges are cancelled. We cannot take. So other possible thing is we can either take this edge and cancel out all the three edges. And again, we cannot take, yeah, sorry. So yes, I'm correct that in this graph, we don't have a perfect match. Why we don't have a perfect matching? Because so that means every vertex is connected to every other vertex. So in this graph, if you take one edge, so suppose I will consider this edge. So if I take this edge in our matching, then obviously any edges which will share the common endpoint. So if you consider this edge, then this edge E2 and E1 will share a common endpoint. This edge E3 and E1 will share a common endpoint. E4 and E1 will share a common endpoint. Similarly, here also E5 and E1 will share a common endpoint, this endpoint, right? E6 will share, and we cannot take any of the edges here. So that means I have to move to either this edge, right? So if I consider this edge, then again I cannot consider any of the edges here. So ultimately, this particular vertex will be abandoned. So there won't
Any
be
one
any
of the
edge.
edge will be working independently, ma'am.
Means?
Like any one of the five should work independently. Like others can group up.
Others can group up. Yeah, that's the thing. So that's why in this graph, we don't have a perfect match. So it's not always the case that we have a perfect matching, as we always have a one independent set. We always have a one vertex cover, but we cannot have a one perfect matching. We always have a matching, but there is not a case that we will find out a one perfect matching. There are several examples. You will take any complete graph. That means any graph in which every vertex is connected to every other vertex. In that graph, you may not find a perfect match. Okay, so that's the main point I want to. Is that clear? What is a matching? What is a perfect matching?
Just to repeat again, perfect match.
Yeah, so in perfect matching, what we want that any vertex from a graph should be the endpoint of at least one of the edges in our perfect matching. So for example, here, if you consider any vertex, so suppose I'll consider the vertex number 6. So then vertex number 6 is the endpoint of edge E4, E3, and E2. So among these three edges, I have E4 in my perfect match, right? So that means this E4 edge will cover the vertex number 6 and the vertex number 7 too. It will cover both of the vertices. So similarly, the vertex, the edge number E1 will cover vertex number 1 and vertex number 2. and E6 will take care of vertex number 4 and 5. So if we have such kind of mapping, then it is known to be a perfect match. Whereas if you consider another matching, so suppose I'll take E1 and suppose 6 E7. So suppose this edge which is connected to 4 and 7 is E7. Okay, so now this is a one kind of matching, but it is not a perfect matching. Right? It is a matching because these two edges are not sharing the endpoints, but they are not covering all the vertices. With E1, we can cover 1 and 2. With E7, we can cover 7 and 4, but 6 and 5 is not covered. So that's why it's not a perfect match. Is that clear?
So perfect match, it seems like it is covering all the edges, right?
All the vertices, not edges.
Okay, all the vertices.
Vertices. As a vertex cover all the edges, so it's a kind of opposite of vertex cover. So that means your matching should cover all the vertices. That's a perfect match.
Okay.
Okay. So now these three descriptions are important. Now let's go to the adjacency matrix. Yes. Any doubt?
The edges which we are taking, they should not share common vertex. Like when we are.
They should not share common vertex.
Okay.
Yeah, this is the condition given.
Which has to be independent, right?
That means independent or disjoint, whatever you want to say.
It should not be any adjacent or kind of, you can say.
Adjacent kind of.
Yes, ma'am.
Okay, so now we'll talk about the adjacency matrices. So what is the adjacency matrix? Again, adjacency matrix and adjacency list in degree of matrix. So adjacency matrix. So you guys are familiar with the matrix. So matrix is nothing but a collection of some rows and columns. So in every row you will put some entry. So matrix is nothing but a collection of entries. And these entries are written in form of rows and in form of columns. Right? So every matrix will have some size here. So what will be the size of a matrix? So the number of rows multiplied with number of columns. This will be the size of a matrix. So for example, if I give you a matrix, so in general, matrix is denoted within this these brackets. So suppose I'll take a matrix, such kind of matrix. So this is the one kind of matrix, and what will be the size here? So there are two rows, correct? There are one row here, another row here. So there are two rows and three columns. So this is a matrix of size 2 by 3. Now in every matrix, we have a precise way to find out the entry. Find out the entry means if you have a matrix, then what will be the entry I, j? So Aij will be the ijth entry. So that means it will be, this is an entry. This is an entry. In the ith row and jth column of the matrix. Right. So for example, in this matrix, what will be the entry A2, 3? So that means in the second row, I have to choose the third column's entry. So in the second row, the third column's entry is 6. So that means A23 is equals to 6. This is actually a precise way for saying what are the entries in a matrix. Okay. And this concept we will use to find out what is the adjacency matrix related to a graph. So what is an adjacency matrix? So adjacency matrix is a matrix of size n by n. So suppose we have a graph with the vertex set V and the edge set E, and there are n vertices. So we know that this symbol denotes the cardinality of a set. So we have n vertices are there. So if a graph has n vertices, then we can actually assign an n by n matrix. N by n matrix means n rows and n columns of a matrix in such a way that we will describe the entry of this n by n matrix that the ijth entry, so that means the entry in the ith row and jth column will be equal to 1 if there is an edge from the vertex number I to a vertex number j. Okay, so if there is an edge from vertex number I to vertex number j, we will tell that the entry in this particular matrix, the ijth entry in this n by n matrix will be equal to 1. Otherwise, it will be equal to 0. And again, so here, as we know that the set of vertices can be anything, cities, or number or people or dance group or anything we can take as a set of vertices. So when we come to the mathematical description of graph, so that means when we talk about the adjacency matrix, then for every vertex we will assign a number from 0 to n minus 1. So that means if we have n vertices, so suppose I am taking 5 cities, let's take Bangalore, Chennai, anything. So every city I'll assign one number from 0 to n minus 1. So if I'm taking 5 cities, so suppose I'll take Bangalore is there, Chennai is there, Mumbai is there, Jaipur is there, Delhi is there, and some another city is suppose Bhopal is there. Okay. So now these are our vertices. So in place of these cities name, I'll assign one number here. So I'll take 0 to be the 0 I'll assign to Bombay, 1 I'll assign to Chennai, 2 I'll assign to Mumbai, 3 I'll assign to Jaipur, 4 I'll assign to Delhi, and 5 I'll assign to Bhopal. So now we can replace the set of vertices, which are actually our cities, to a set of numbers. So that means we can take 0, 1, 2, 3, 4, 5 to be our vertices. It won't change the graph because we are actually relabeling the vertices. It doesn't matter. So ultimately, in every graph, we can actually take the set of vertex to be equal to this set, 0 to n minus 1. Okay, so that's why this description makes sense. If there is an edge from I to j, then we'll take ijth entry to be equal to 1 in our matrix, and otherwise we'll take 0. Now suppose we have a very simple graph here. So I can take any of the graph. So suppose we have this graph. This is an undirected graph. Okay. In directed graph also, we will do the same thing. If there is an edge with starting from vertex number 1 and end at vertex number and end at vertex number b or I comma j we can use, then we will take 1. Otherwise, we will take 0. Then capital A of I comma j equal to 1. Otherwise 0. Okay. So suppose this is our graph. So here are vertices 1, 2, 3, 4, 5, 6, 7. Right. So if I want to make an adjacency matrix, then it will be a 7 by 7 matrix because there are 7 vertices. Right. Either you can start from 0 or you can start with 1. So in our lectures, we start from 0. Here I'm starting from 1. That doesn't matter for me. The size will always, how many numbers are there. So let's take it 7 by 7 numbers. Okay. So what will be the first entry? So first entry will be, if there is an edge from 1 to 1, then I'll take entry here to be equal to 1, otherwise 0. But we know that we are not considering the self loop. That's why the entry will be 0. Now what will be the second entry? So here we have 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Okay. So 1 is connected to 2, so that's why this entry will be 1. 1 is connected to 3, that's why this entry will be 1. 1 is connected to 4, that's why this entry will be 1. 1 is not connected directly to 5, so that's why this entry will be 0. And 1 is not directly connected to 6, that's why 0. And here we have 1. So in this way, we can actually associate a matrix to a graph, and that matrix is known to be an adjacency matrix. Is that fine, adjacency matrix?
Yeah, it's fine.
Yeah, kind of easy. Right. And the second description is the adjacency list. So again, why do we need such kind of mathematical description? Because here we are just dealing with a very simple graph. Simple graph means either we have a 10 vertex or 12 vertex. But in practice, when we consider a real life problem, then there will be 1,000 number of vertices or more than that number of vertices. So we cannot handle those vertices just by using pictures. Right. So that's why this matrix will give us a way to compute or to run a program, because in a program we need some mathematical structure. We cannot put a picture and tell him to compute it, right? We need some mathematical structure to be present there and then apply and then run something over this. We cannot run any algorithm or any program over some picture. That will be very difficult. So it will be very easy if we have some mathematical description for that. And it is very easy if we have a matrix there. So that's why we are describing a matrix related to a graph. And the second description is adjacency list. So list is nothing but you have to make the list of every vertex and the neighbor of that vertex. So suppose the vertex number I will be here, and the neighbor of that vertex will be here. Whatever the vertex is connected to I directly. Okay. So what all those J you have to connect in such a way that there is an edge from I to J. So this list is known to be an adjacency list. Now, there are several cases where adjacency metrics will be much more easier to handle. And there are some cases where adjacency, using adjacency list is much more useful. Those two things we will learn when we talk about the complexity of BFS and DFS process. Okay. So for
So,
today,
so ma'am,
yeah.
for week number 10,
Mhm.
you have to study until adjacent matrix.
No. We have BFS, DFS, and topological sorting, I guess.
So when
So
you
these,
will study?
yeah, tomorrow we'll study because I actually
Oh, okay.
exhausted those
It's
with
already 10. Oh, I didn't watch the
yeah.
time.
And also we have some doubts about quizzes and all. So I'll take those and we will continue in the next session too. Okay, so don't worry about that.
Ma'am, the next session would be like starting of BFS and DFS, right? Like till there you have
started
completed,
from
right?
BFS, DFS,
Okay.
and topological sorting. It will take 1 hour at most.
Ma'am, when you will schedule tomorrow's session?
Session is scheduled. I don't know.
Already is there, scheduled session.
Already is there, no?
No.
Sorry, not there. Sorry,
Saturday,
Not there.
it's not there.
Not
It's
there.
not there?
No.
Just a second, I'll let you know. Preferably, I mean, it will be on Saturday.
Tomorrow is the deadline for week 10.
Yes, ma'am. That's
Yeah,
confusing
actually,
actually.
tomorrow is the deadline for week 10.
Like in this week, we should start doing week 10, and the next week we have to end week 11. Then the portion is completed. But it's a bit like
So
it's
tomorrow only we
asking
will
us to
have a
copy
session.
and write.
Yeah. So if
Manish,
there is no
if you would
session
say
tomorrow,
that, you would say right, we can manage. Right now, can't manage.
Yeah, but that's the reality which is happening.
but graph
Okay.
theory have to
I
learn.
mostly
Have to
never do,
learn
but I
currently.
have to do that actually.
Okay.
Yeah, can't help.
Yeah, tomorrow we will schedule a session. That session we will, we will just.
But ma'am, after your session, just 2 hours will be left. We have to take lunch, and after that, solving the
Lunch or
entire grid
dinner?
assignment. Oh, dinner. After the dinner.
Okay.
It's quite difficult.
Okay, so what can I do? We can
Is there
schedule a
any
session in morning.
ma'am. Is there any
That-
changes in deadline, or is it fixed at all?
No, there won't be changes in deadline.
Ma'am,
Actually, it's not in our hands. So
Can you take session in the morning?
yeah, I can take because the deadline is tomorrow. So the deadline is 12 p.m. So right, 12
Ma'am,
p.m. is the deadline.
which time you will schedule?
Yeah.
Because I have to prepare before.
I have to ask Vishal sir about this, but preferably in morning 7 to 9 maybe.
Ma'am, that's a bit too early.
Ma'am, 7 to 9, but early, not early, because
8 to 10.
we study late night. That's why it's early.
Yeah, even that's the problem. It's winter
No,
season.
afternoon is slot is free. 3 o'clock, 2
Yes,
o'clock slots are free.
your wish, ma'am.
Okay,
Please.
okay. I'll
We are
talk
not
to Vishal sir
forcing
about
Or
this
ma'am,
and
let it be. You can take.
Same time if possible.
Ma'am, let it be now. We have to manage this week for this week. What we can do? You can take from 8 to 10.
Yes, ma'am. Please.
Because,
We can manage. No problem.
because if
Okay,
we do
fine.
such things, unnecessary bias will be created.
Yeah, fine. So let's stick with 8 to 10. So tomorrow, BFS, DFS is not that tough. I mean, it's just a process, just a method. I hope you guys won't be struggling because these concepts are a little bit confusing, matching independent set vertex cover. But BFS, DFS are very straightforward. There you just have to follow a procedure.
Ma'am, once you
Ma'am, we have
can
not-
review your entire slide one by one, just quickly, for a quick revision of this week.
Before that, ma'am, actually tomorrow from 6 o'clock it slots are free only.
Okay, 6 to. Okay,
And
I'll talk to
moreover,
Vishal sir about this.
deadline as on tomorrow. Just to complete these topics and we'll start this solve with the problem. Solve with the session also pending for week 10, right? So after deadline, there is no use of solve with this problem of week 10. So 1 hour will take for this one and 1 hour will finish that one solve with us. Then it would be more helpful if it is possible.
Okay. So either what we can do, I'll just take more now half an hour more and just quickly explain what is BFS, DFS.
Okay.
And
Tomorrow you
we
take
also
solve
have
with us.
topologies. Tomorrow we'll just focus on solvers and whatever doubts
Okay.
you have. So
That
for
would be
now,
great.
time being, we can postpone the quiz questions. Okay.
Yes, ma'am. Please, no
Excuse me,
problem.
ma'am. Is there any group to connect with you?
No, actually, a group, I don't have any. You can connect with me on Discourse. That is one possible way.
Ma'am,
Other than
Ma'am, where
For
is
that,
this
we need
discourse, ma'am? Like what is the site? I have not
Discourse, you have
come
Discourse
across.
ID. You guys will have one ID that is known to be a Discourse ID.
we did not receive anything still yet. I did not receive.
You
You
have to
won't
check the
receive?
Yes, ma'am.
mails.
you have to check on your portal because which person have the roll number, he must have the discourse.
It is available
Yeah.
in your course page. No, you can see there is a link in course
Yeah.
page.
Okay.
Okay, sir. Thank you. I'll just go through it.
Please finish this fast, yes.
Yeah,
Yes,
I'll just
ma'am. Yeah,
download the
please,
slides
please.
and we'll go by slides. BFS, DFS, and topological sorting. We have three topics, right? Just give me 1 second. In week 10, do we have DFS numbering too?
Yes, ma'am, we have.
Yes, ma'am.
So let's at least try, at least we can complete BFS and DFS. Then in the next session, we'll go for numbering, because numbering is important. That will give us a way to find out forward and backward edges. So let's start with what is a BFS process. So in BFS process, what is the main purpose of this process is, we want to answer the reachability question. Reachability question means if we have a graph, then can we move from one vertex to another vertex, or we can find out a path from one vertex to another vertex. So for example, this is your graph. So this graph represents the airline networks. So that means this is a one airline company which is serving over these number of cities. So here every vertex is denoted by one city. There is a direct flight from vertex number vi to vertex number vj, then there is an x. So in this way we are formulating this particular graph. Now here we want to answer that can we reach from one vertex to another vertex or not. So or can we schedule a sequence of flights from one city to another city or not. So BFS will give us a very feasible method to find out about this kind of reachability. Okay, so in BFS, what we do, so all those things are okay. So I'll explain all those stuff. So in BFS, mainly we will account two things initially. So we'll account the visited vertex, and then we will account the queue of all explored vertex. So what are those things? So let's see. So what are the visited vertex? Okay. So visited vertex means those vertex which are on which we are going to visit. So in BFS process, what happens? We will start with one vertex, and we will visit the neighbor of that particular vertex, and then we will explore them. So what is the meaning of exploring a vertex? The meaning of exploring a vertex means we have to we have to visit the neighbors of that particular vertex. Okay, so all those things we'll see when we look into the example. So visited vertex means those vertex which we can reach from our given source vertex. So again, BFS process will start from fixed vertex. So whatever vertex you want to take, you can take that vertex as your source vertex, and then we will explore the neighbor of that particular source vertex, and then again we will explore the neighbors of those source vertex. Okay, so for that we have a feasible method in this way. So suppose we'll start our BFS method from here. Okay, so here what happened again, we have to take care of two quantities, the visited vertices, and we will use Q for manage our unexplored visited vertices. So that means all those vertices which we already visited but haven't been explored. Explored means we haven't gone through the neighbors of those vertices. So we'll write down those vertices in a queue format. So what is a queue? So queue is one way to arranging a sequence. So if you have any numbers and you want to arrange them in a sequence, so there are two ways. So either you can use a queue or you can use a stack. So queue uses queue based on a principle of first in and first out. So that means whatever number number will be at the first place of your queue, that number will get explored first, and after that whatever in the second place, third place, and so on. And the BFS process will stop when our queue is empty. Okay, so let's work on an example. So suppose this is a graph is there, and now we want to apply a BFS scan on this particular graph starting from the vertex number 7. So what we'll do, so now 7 is our vertex, right? So that means, okay, so we'll start with vertex number 7. So what we do, so initially we will enter the visited, we'll change the status of vertex number 7, the visited status of vertex number 7 from false to true, and then we will add that vertex number 7 into our queue. Again, we will add all those vertex in our queue which we want to explore. Okay, so since 7 is visited and it hasn't been explored, that's why it's on queue. And after, so whenever we have a vertex in our queue, we can actually explore that vertex. So now what we will do, we will mark 7. Yeah, we have done this step. We mark 7 and add it to our queue. Now next step will be, we will explore 7. Now what is the exploration of a vertex means? We have to visit its neighbors. So that means we have to visit the neighbors of 7. So what are the neighbors of 7? So 4, 5 and 8 are neighbors of 7. So now we will change the status of 4, 5 and 8 from false to true, and all these vertices into our queue for exploration, right? Because these are the visited vertices which haven't been explored. What is the meaning of exploration of a vertex? That we have to visit their neighbors too. So here we will add 4, 5 and 8 into our queue for exploration. But here observe that we have visited 4, 5 and 8 at a single glance of 7. So that means when we explore 7, we take account of 4, 5, 8 at the same time. So in your queue, you can actually write this 4, 5, 8 into some other format. So you can write it to be 4, 8 and 5, 8 and 4. You can write to be 8, 5 and 4. It doesn't matter. All things are same. So here you have a choice that you can actually write these three numbers in any order you want. But again, in graph theory, we always take this convention that whenever we are writing a numbers where we have choice, we will take the smallest one to be the first, and then largest, and then largest. So among 4, 5 and 8, the smallest one is 4. So that's why we are taking 4, and then 7, and then 8. This is a general convention. It's not necessary, but it will make, it won't, we don't have to spend too much time on thinking that which vertex we have to write down first. Okay, so just a general convention. So we'll now 4, 5, 8 are the vertices which are visited but haven't been explored yet. So the next step will be exploration of 4. Why the exploration of 4? Because 4 is in our queue's first place, right? This is the first place of our queue. First place. So whatever vertex is there in the first place, we will explore that vertex first. So now we will explore 4. So what is the meaning of exploration of 4? Exploration of 4 means we have to collect the neighbors of 4. So what are the neighbors of 4? 0, 3 and 7. So as we explore 4, we will visit 0, 3 and 7. But 7 is already visited. So that's why we cannot, we won't take any account of 7. We'll just take 0 and 3. So now 0 and 3 status will change from false to true. So this is 0, this is 3. And again add 0 and 3 in our queue. But again, since we are exploring 0 and 3 in a one glance, so it is okay if you write 0, 3 or 3, 0. But again, because of our convention that we will write the least number first and then the largest one. So that's why we are writing 0, 3. So now what will be the next step in the BFS? So the next step says whatever the vertex is there in the first place, explore that vertex. Okay, so now we will explore 5. So what will be the exploration 5 means? Exploration of 5 means we have to visit the neighbors of 5. So what are the neighbors of 5? So the neighbors of 5 are 3, 6, 8 and 7. So now we have to take care of all those neighbors. But here 7, 8 and 3 are already being visited. So that's why we won't account 7, 8 and 3. We'll just take the account of 6. So we'll say that 6 is now visited. So that's why we'll change the status from false to true and add that 6 in our queue for exploration. Okay, so now what will be the next step in this BFS? Can you guys explain? What will be the next step now?
So what are the left out?
Now
We
we'll
have to
check.
explore it.
Right, we have to explore 8, right? So now we will explore 8. So what is the exploration of 8 means? Which vertex now we will visit if we explore 8?
9,
9.
5, 7.
Correct, because 9 is the only new neighbor 8 has, because 7 and 5 are already visited. So that won't give us any new information. Only 9 will got visit now, and 9 we will add into our queue. Now again, the next step will be exploration of 0. Now which vertex we will visit when we explore 0?
1 and 2.
1 and 2, correct? Because they are the neighbor of 0. So the exploration of 0 will give us that 0 and 1 and 2 are now visited. And since they are visited vertex, we will enter them into our queue for exploration. Okay, and again we can write 1 and 2 or 2 or 1, just depend on our convention. Since 1 is smallest, so that's why we write 1 and 2. Now the next step says explore the vertex number 3. But again, all the neighbors of vertex number 3 are already been visited. It won't give us any new information. So that's why exploration of 3 won't give us anything. So exploration of 6 also won't give us anything. Exploration of 9 also won't give us anything. Similarly, exploration of 1 and exploration of 2. All those things won't give us any new information. So now, since our queue is empty, now we can stop our BFS scan. Okay, so this is the basic BFS method. Is that fine? So I'll repeat what are the steps we are doing. So we'll start a vertex. So we will start with a vertex.
It can be any random vertex.
Yeah, it can be any random vertex. I have chosen 7, but you can choose anything else. Okay, so start with one vertex, and that vertex will be your source vertex. Okay, so start that vertex and add that vertex into our queue. Right, now explore that vertex. Follow that vertex. So explore that vertex means you have to visit its neighbor. So change the visiting status and add all the visited vertices in your queue. Change the status and add it into your queue. Okay, and now in our queue, we'll take first come, first out principle. So that means whatever vertex is here, we'll explore that vertex next and repeat this process until all the members of the queue get explored. That means queue get empty. So when our queue is empty, we'll stop our BFS. So this is a BFS scan. So if the process is not clear, just go it, try it by yourself. Just download the PDF and try to think that what is the next step we are doing. Okay, that will be helpful. Is there any doubt in BFS now? Any thoughts?
Ma'am, if
How can
I'm
we draw the
starting,
equivalent?
One by one.
if
Yes,
the
Lokesh.
source is like, yeah, sorry.
Sorry, yes, Alengu. You can
Yeah,
go.
so if we start with the 7, explore 7, so I'm taking out 4 and 5, 4 and 5, 8. So next, so it is already have to check with 4, right? Because it is at first. So I have to check with the 4.
First.
So
Right.
3 and 0, 3 and 0. Next, I supposed to choose 5. Why? Actually, why
Yeah.
not 3?
Because it works in a queue principle. What does queue says? So queue says first in, first out. So after 4, we enter 5. We enter 4, 5, 8. And then after these number, we entered 0, 3. And then 6, 9, 1, and 2. So this is our queue. So queue says first in, first out. So after the exploration of 4, we have to explore 5, then 8, then 0, then 3, then 6, then 9, then 1, and then 2. The queue is a
Okay.
sequence. So we have to consider the order.
Okay, ma'am. Thank you.
So ma'am, we have to maintain the order.
Yeah. In which order we have explored the vertex, that order we have to maintain. So you cannot explore 0 before exploring 5. First you have to explore 5 and then explore 8 and then you can explore 0. But you can interchange between 5 and 8. That's not a problem because we are visiting 5 and 8 at same time. But we cannot change the order of 5, 8, 0, right? Because at a time we are
it's quite like we are visiting each and every point as a sequence, and we are incrementing that it's true. It's quite Boolean algebra,
something like that you can think. But this is the typical BFS method, the standard BFS process.
Excuse me, ma'am.
Okay. Yes, Vishnu.
Ma'am, when we explored 3, at that time also QE that was empty. QE. So can't we stop?
No. When we explored 3, see, when we explored 3, the queue is not empty. There are members in a queue. 6 is there, 9 is there, 1 is there, and 2 is there. So that's why we have to explore. Although these exploration won't give us anything new, but that's the procedure of BFS. In this graph, the exploration of this vertices are not giving us other information. But it is possible that there are some other vertices in some other graphs. So that's why we have to follow the procedure, standard procedure. So that's why after exploring 3, we have to explore 6, then 9, then 1 and 2. Okay, so that's all. 9, 1, and at the last 2. Okay, is that fine?
Ma'am, how can we draw
Lokesh, your voice is not clear.
map for this? Yeah, ma'am, am I audible, ma'am?
Yeah, now you are audible.
Ma'am, how can we draw the equivalent map for that process, ma'am? I understand the process, but I don't know how to draw the process.
See, so for every BFS process, there is one tree attached to this BFS process. So this is known to be a BFS tree. So I am not sure you guys are familiar with tree now. So what is a tree? So tree is nothing. So I'll explain here. So what is a tree? So tree is just a special type of graph. So it's again a graph. But what type of graph? It has two properties. So first property is it will be a connected graph. And connected graph, but a minimally connected graph, not only connected, but minimally connected. Okay, so what do we understand by minimally connected graph means? So from this graph, from this particular graph, if you add one edge, it will create a cycle. And if you remove one edge, it will disconnect the graph. So for example, if I consider this graph, okay, so suppose we have this graph with some vertices. Now in this graph, what is happening? This is a minimally connected graph because here, if you add one edge, so if you add any edge at any place, so suppose I'll add the edge between the vertex number 2 and vertex number 3, then addition of this edge is actually creating a cycle. So this is one criteria. And another criteria is if you remove any edge. So suppose I'll remove any edge you can take. So suppose I'll remove this edge. Okay. So if you remove this edge, then it will disconnect your graph. The graph is disconnected because this vertex number 6 is not connected to any other vertices. So such kind of graph is known to be a minimally connected graph. And those minimally connected graphs are nothing but trees. Okay, so you can understand by tree is nothing but a minimally connected graph, or we can say a graph, a connected graph
Acyclic graph.
is acyclic, right?
Yeah.
So acyclic means there is no cycle in this particular graph. So such graph is known to be tree. Now for every BFS process, we can associate it a tree to that particular BFS process. How we'll associate? So in a tree, there will be one root. Right? So here, if in this tree, you can take root to be any vertex, it doesn't matter. But in BFS process, since we are exploring the vertex level by level, so what will happen? So in this process, we have started our BFS process from vertex number 7. Right? So let's just want to find the space. Okay. So here we started from vertex number 7. Now, the exploration of vertex number 7 will be the cause of visiting of vertex number 4, 5, and 8. Correct? Now the exploration of 4 is the cause of visiting the vertex number 2 and 3. Now the exploration of 5
Ma'am,
is the cause of...
vertex number 4 is not 2 and 3, 0 and 3.
No, when we explore 4, we visit vertex number 0 and... Oh, sorry, 0. When we explore vertex number 4, we visit the vertex number 0 and when we explore vertex number 5, we visit the vertex number 3. 3 is already been visited. We visit only one vertex, that will be 6. Yeah, so here there is only one vertex, that is 6, right? So ultimately, I am just making a tree by in the format that we actually gone through the BFS process, right? First we visit 7, then explore 7. So exploration of 7 will give us the visit. It will change the visited status of 4, 5, and 8. Exploration of 4 will change the visited status of 0 and 3. Exploration of 5 will change the visited status of vertex number 6. And exploration of 8 will change the visited status of vertex number 9. Okay, now exploration of 0 will change the visited status of vertex number 1 and 2. Exploration of 3 will change the visited status of nothing, right? It won't give us anything new. Similarly, 6 won't give us anything new, 9 won't give us anything. So now this is a tree. If you observe, then this is a tree. And this is the tree associated to, and this is also known as to be BFS tree.
This is a good explanation. Yeah.
Yeah. So this is a BFS tree. Now here, there are some questions. I think you guys are already been gone through the questions. So what happened? They will ask you, I mean, the one BFS tree is given to you, and they will ask what are the edges possible in the graph and not possible in the graph, right? Some questions are there. So here, what is happening? So suppose there is an edge between any two vertices which are situated at different levels. Again, we will understand about the levels. So what are the levels? So in BFS process, we will apply some levels. We will append some levels. So initially, the level of source vertex will be 0. And whatever the vertices we are exploring, because of the source vertex, those will get the level number 1, right? And those neighbors will get the level number 2, and those neighbors will get the level number 3. Okay, so these are the levels associated to each vertex. So that means 4 has level number 1, 5 has level number 1, 6, 8 has level number 1, 0 has level number 2, these all has level number 2, and these has level number 3. And this will start with level number 0. Now, there are some questions which will ask you that if this is a BFS tree, then what are the edges are not possible in the graph? Okay. So now observe that BFS tree, how it happens. So if you take an edge, so I'll ask you a question. Is it is 2, 5 an edge in our graph, in graph G, right? Something like that. So that means you have to
No.
judge that such kind of edge is present on. So obviously, right, the answer is correct, no. Because if 5 is related to 2, so suppose 5 is related to 2, so then when we explore 5, we also we have to visit the vertex number 2. So if there is an edge between 5 and 2, then this vertex will come into the level number 2. It won't be in level number 3. So in general, whenever the vertices are one level different from the other vertices, so that means, see, vertex number 5 is of level number 1, and vertex number 2 is of level number 3. So it is not possible to connect such kind of vertices which are situated. I mean, there is a one level difference in between them, right? So we don't have such kind of edges in our graph. So this is one thing you can take as a remark for solving question, because there are questions which will ask you such kind of things. That is it possible to draw an edge from 2 to 5 in our graph or not by just observing the BFS tree. Is that fine?
Ma'am, can we, like, if the question would have been that is there an edge between 5 and 3?
So then it is possible, right? Because if there is an edge between 5 and 3, still the exploration of 4 will give us 0 and 3. So suppose you will just make an edge in our graph. Okay. So yeah, there is an edge between 5 and 3 here.
Yes,
Originally
ma'am.
there is an
Like,
edge.
it is visible in the graph, but like when we draw this tree diagram, there we have associated 3 with 4 and not with 5.
Yeah, so that's our choice, because see, in the queue we are listing 4, 5, and 8. So that means first I'm
Yes,
observing
ma'am.
4,
What
then I'm
comes
observing 5,
first
and
will
then
be. Yes, ma'am. Ma'am, that's clear. But actually, like, if a person looks only at the tree diagram and not at the original graph, then how will he understand that this was actually associated, this tree was associated with 5? Then
correct.
he would.
So see, so that's why they will. So see, I mean, for any graph, there are several VFS trees because of these kind of choices. So here you can make the choice that you can either visit 4 first, you can either visit 5 first or 8 first. So that's why for any graph, the BFS trees are different. It depends on the person to person. But you can answer, but it is possibility. They are just asking you about a possibility that it is possible or not. So obviously, such kind of thing can possible. You can answer this by just taking an example. So just draw. Okay. So what you can do? See, these two vertices are only one level difference. I mean, this is at level number 1. This is at level number 2. So it is possible to have an edge in between them.
Okay, so if the difference is like it's more, then we'll say that it's not possible, like in case of 2 and 5. But since here the difference is of only one level, so we can say that.
Right. Because then
Ma'am,
only
it may
this
be
2 should come
possible.
here. Sorry?
Ma'am, it may be possible, but not sure to have that edge right now.
Right. So this edge can be possible. Yeah, this edge can be possible. You can draw any edge in between them. This is also can possible because we can actually draw an edge and now we can
5 to 0 may not be possible.
5 to 0 is also can possible. It's not the case. 5 to 0 is also can possible because we are choosing the exploration of 4 ahead in place of 5. So that's why this is possible. So just think about it. So if the vertices are situated in such kind of level, so that means the level are just only +1. Then in this case, every edges can possible. So that means there will be a graph whose BFS tree is this tree, and there is an edge between 0 to 8 to 0 to 8. This is also possible, but we cannot jump from one level to level number 1 to level number 3. Okay, so this is not possible, but the simultaneous level or the consecutive levels are possible. The jump of one level, so those edges won't be there. Are you getting my point? What I want to say?
Yeah, ma'am. Yeah.
Yeah, just think about it. You will get the motivation. You will get the intuition how this is going to work.
Ma'am, where can we see the application of this process?
Reachability question. See, if you want to answer that some vertex is reachable from some vertex or not, what you have to do, you just have to apply a BFS scan, and if this visited status remain false only, then in that case, that vertex is not reachable from any other vertex, because we are changing visited status from false to true. Only we are reaching at that vertex, right? So
We're looking
we
for all
started
the
from
vertices. Yes, ma'am, which would have an edge between the. Yes, ma'am, it's clear.
correct. Yeah. Now in BFS, we also account two more things, that is a parent information and the level information. So I'll explain both using one single step. So parent information is nothing but that vertex from which we are reaching to that particular vertex. For example, the visiting of 4, 5, and 8 is only possible when we start the exploration of 7. So whatever the reason, whatever vertex we want to visit, so we have to find out that vertex which will cause the changes of in the visiting state of vertex. For example, the parent way of the vertex 4, 5, and 8 will become vertex number 7. And initially, in the start of BFS process, we'll just append the level every vertex to level -1. And we start with the source vertex, and then we'll append the level to be equal to 0 to our source vertex. Again, we'll add it to queue, we'll explore 7. As we explore 7, we'll visit 5, we will visit 4, 5, and 8. So now we will change the level of 4, 5, and 8 from 0 to 1. Okay, because 7 will be of level 0, 4, 5, 8 will be of level 0 plus 1, which is equal to 1. Again, 0 plus 1. And again, this is 0 plus 1. And the parent of 4, 5, 8 will become vertex number 7. Okay. Now, similarly, the parent of now if we explore 4, we will visit 0, 3. So that means the parent of 0, 3 will be the vertex number 4, and the level of 0, 3 will be the 2 level. And you are here you can observe that whatever level we have described in this particular tree, those level and this level is actually same. But because it just telling us that how many steps we need to reach those vertices from our source vertex, correct? In the 0 step, we are at our source vertex. In the step number 1, we are at vertex number 4, 5, and 8. In the step number 2, we are at vertex 0, 3. Okay, so the same thing. So again, the exploration of 5 will give us the will change the visiting status of 6. So that's why the parent of vertex number 6 is the vertex number 5, and the level is 2, because we are visiting it at the second step. Okay. Similar with 8 also. So the parent of 9 will become 8, and it will be of level number 2. These level are very easy to understand when we draw the BFS tree, because there one line will denote the one level. Okay. So the same thing is here. So that's all of this BFS. Is there any doubt? Yeah.
Unless we don't visit all the vertices, we can't end that process.
We can't end
Or
that
is there
process. That's the until and unless the queue is empty, we cannot end our BFS process. That's the procedure.
matlab, there is no way to end that process in between.
No, there's no. one particular BFS scan will end only if the queue is empty.
Yes, ma'am.
Okay, so we will discuss BFS tomorrow because I don't know. Because DFS numbering is also there, so we'll discuss both things together. I or someone else will discuss both things together and topological sorting. Is that fine for you guys?
Ma'am, when are you going to be conducting tomorrow session? At what
That
time?
I'll let you know in the possibly in the morning. I have to discuss with Vishal sir about this. That's all.
Excuse me, ma'am. There's a small request. Can you please take next session? Like, can you only please take next session?
I'll try to take the next session tomorrow. Okay, I'll try to take the next session.
Yes, ma'am. It will be more helpful.
Yeah, but again, I have to talk with them. So, what is the case?
Yeah, ma'am. If you can take, it will be more helpful for us.
Okay, yeah, right. Although, yeah, I know that this week is actually very long and it's a new concept to you, new thing to learn, and there are so many concepts DFS, vertex cover. So it is a little bit hectic, but this is the thing you have to do. So you cannot skip it. That's the procedure.
Yes,
I can understand for such a I mean, this topic is very interesting. If you go into the depth of graph theory, it's very interesting because it is highly applicable. You can find a real life example at everywhere. But again, you need time. Okay, so thank you guys for joining. So we'll see you in the next session.
Thank you so much.
Thank you, ma'am. Thank you so much.
Thank you.
Good night.
Thank you, ma'am.
Good night, bye.
Thank you, ma'am. Bye, ma'am.